Hi everyone, and welcome to this C++ course where we're going to learn how to use C++ for machine learning. My name is Martin Yanev and I'm a professional software engineer and a computer science professor at Fitchburg State University. So in this course you will learn how to use C++ to train AI models, how to use supervised and unsupervised learning. We will cover and implement core AI algorithms like regression, decision trees, clustering, and neural networks. I will also show you how to optimize your models, handle real-world datasets, and most importantly, how to integrate those models into high-end C++ applications. By the end of the course, you will learn how to implement and deploy efficient machine learning solutions with C++. You will also find in the description the full code for this course in a GitHub repository. So make sure you like this video and you also subscribe my channel for more similar and most importantly free courses like this one. So now let's jump straight to the course.
Machine learning, or ML for short, is a fascinating area of artificial intelligence that empowers machines to learn from data and improve their performance over time without being explicitly programmed. This video will delve into the fundamentals of ML, exploring what it is, the types of tasks it can solve, and the approaches used in the field. By the end, you'll have a solid understanding and even a taste of coding with C++. To start, machine learning can broadly be defined as a set of techniques that enable computers to learn from past experiences or data. Unlike traditional programming, where explicit instructions dictate the program's behavior, ML algorithms identify patterns in data, which they then use to make predictions or decisions without human intervention. Think of it as teaching a child. Instead of telling them exactly which actions to take, you show them examples from which they can draw conclusions and learn. When we're talking about the tasks that can be solved with machine learning, the possibilities are vast. These tasks include classification, where we assign labels to input data, regression, which predicts continuous outcomes, clustering, which groups similar data points, and reinforcement learning, where an agent learns optimal actions through trial and error. Each of these tasks has a unique application, enabling everything from spam detection in emails to recommending your next favorite movie on streaming platforms. Now let's see how we can implement a simple decision tree algorithm to classify emails as spam or not spam. We begin by defining a decision tree class that encapsulates our classification logic. Within this class, we create a public method called classify, which takes an email's content as a parameter. The method uses the find function to check for the presence of specific keywords associated with spam, such as discount and buy now. If either keyword is found, the method returns spam. Otherwise, it returns not spam. In the main function, we create an instance of the decision tree class and proceed to define a sample email containing the keyword discount. We then call the classify method on this email and output the classification result using std count. This straightforward implementation highlights the basic functionality of a classification algorithm, demonstrating how a few simple rules can be applied to make decisions based on the content of the email. By following this structure, students can grasp the fundamental concepts behind classification tasks in machine learning. Next, we will write a simple implementation of a linear regression model in C++. In this code, we define a linear regression class that encapsulates the core properties of a linear regression model, the slope and the intercept. The constructor of the class initializes these two parameters, allowing us to set the line that will be used for predictions. The predict method takes a single input representing a feature of the house, specifically its size in thousands of square feet. The method calculates the predicted price using the linear equation, which is simply the product of the slope and the input, added to the intercept. This structure effectively captures the relationship between the input feature and the predicted output. In the main function, we instantiate an object of the linear regression class with arbitrary values for slope and intercept, representing a trained model. We then define a sample size of 2.5 and call the predict method to receive the predicted house price. The result is printed to the console, showcasing how this simple model can estimate real-world values based on learned parameters. This implementation serves as a foundational example of regression in machine learning. Now let's see how we can implement a simple k-means clustering algorithm in C++. We start by defining a class called k-means, which takes the number of clusters as a parameter during initialization. Inside this class, the fit method is responsible for the core functionality of the algorithm. Here, we initialize the centroids by randomly selecting a number of data points equal to the number of clusters. This is a crucial step since the centroids serve as the initial estimates around which the clustering will occur. The getCentroids method allows us to retrieve the current centroids after fitting the model to the data. It returns a vector containing the coordinates of each centroid. In the main function, we create an instance of our k-means class, specifying that we want 3 clusters. We then prepare a simple dataset with 6 2D points for the algorithm to work with. Following this, we call the fit method with our data points to perform the initial centroid assignment. Finally, we retrieve the centroids and print them out. While this example simplifies the k-means algorithm by omitting the iterative adjustment step for centroids, it successfully showcases foundational concepts in clustering, illustrating how data can be grouped based on similarity. Now let's take a look at a simple implementation of a reinforcement learning agent using C++. This code defines a class called SimpleAgent, which mimics how an agent interacts with an environment to learn from its actions. When we instantiate this agent, it initializes a random seed to ensure varied behavior each time it runs. The act method allows the agent to make a decision by randomly choosing between 2 possible actions, typically denoted as 0 or 1. This random decision-making is fundamental in reinforcement learning, as it allows the agent to explore different actions and their associated rewards. Next, the learn method takes 2 parameters, the action taken and the reward received. In this simple implementation, it merely prints out the action and reward to the console, but in a real-world scenario, this method would ideally contain logic to update the agent's knowledge based on the feedback from its environment. In the main function, we create an instance of the agent and run a loop 10 times, simulating the agent's action and reward process. An action of 0 receives a reward of 1, while an action of 1 receives no reward. This feedback loop is essential for the agent to improve its decision-making over time. We've covered a fair amount of ground, but the approaches and tasks within machine learning are extensive and ever-expanding. Whether you're classifying images, predicting stock prices, or recommending content, the principles we've discussed will serve as cornerstones in understanding this exciting field. From supervised tasks like classification and regression, to unsupervised approaches like clustering and reinforcement learning, each has unique applications in real-world scenarios. As we continue to develop applications using machine learning, remember that the most important part is understanding the data and the problem we're trying to solve. With the basics in hand, you're well on your way to diving deeper into more advanced topics and real-world implementations. Always keep experimenting, iterating, and enjoying the learning process. So gear up and embrace the future of technology. The world of machine learning awaits, and who knows, maybe your next project could bring about the next big breakthrough. To understand machine learning algorithms, a firm grasp of certain linear algebra concepts is essential. Today, we will explore the critical elements of linear algebra that form the backbone of various ML techniques. So far, we learned that machine learning, ML, enables machines to learn from data and improve without explicit programming, covering key tasks such as classification, regression, clustering, and reinforcement learning. We explored these tasks with examples and C++ implementations, including classification of emails, predicting house prices, clustering data points using k-means, and simulating a basic reinforcement learning agent. Understanding these foundational concepts allows for deeper insights into more complex ML applications. As we progress, it's essential to keep experimenting and refining our approach to ML challenges. Let's dive into the world of linear algebra. Linear algebra deals primarily with vectors, matrices, and linear transformations. It serves as the mathematical language that helps describe and manipulate data geometrically. If you think about data in a machine learning context, you'll find it inherently represented in multidimensional space, where each dimension corresponds to a feature of that data. At its core, understanding how vectors and matrices operate will make it easier to understand ML algorithms and their performance. Now let's see how we can implement a simple vector class in C++. This class uses an initializer list to store its elements in a private vector named data. The primary feature of this class is the magnitude function, which computes the length of the vector by summing the squares of its components and returning the square root of this sum, following the Pythagorean theorem. For example, in our main function, we create a vector instance with components 3, 4, which we know from geometry has a magnitude of 5. The class also includes a display method, allowing us to print each element of the vector to the console. This is useful for visualizing the components of the vector, aiding in understanding how they relate geometrically. When we run the main function, we will see the displayed output of the vector and its calculated magnitude. By encapsulating vector functionality within a class, we pave the way for more complex operations and enhanced manipulation of vectors, which will be particularly important as we delve deeper into machine learning algorithms that rely on these foundational concepts. Next, we will write a function to compute the dot product of two vectors. This operation is fundamental in various machine learning algorithms, as it helps determine the relationship between data points represented as vectors. In our C++ implementation, we define a function called dot product that takes two vectors of doubles as input. It initializes a result variable to 0, which will accumulate the sum of the products of corresponding elements from both vectors. As we iterate through each index of the vectors, we multiply the elements of the first vector by the elements of the second vector and add the product to a result. This loop continues until we've processed all elements in the vectors. Once the computation is complete, we return the final result, which represents the dot product. In the main function, we create two example vectors, a and b, filled with sample values. Then we call our dot product function with these vectors as arguments, and the result is printed to the console. By running this code, students will see how the dot product is calculated, offering insights into its significance in understanding relationships between vectors in machine learning contexts. Now let's see how we can implement matrix multiplication in C++. This function begins by taking two matrices, A and B, as input parameters. We first determine the number of rows in matrix A and the number of columns in both matrices, which are crucial for performing multiplication. The result matrix is initialized with the same number of rows as A and columns as B, filled initially with zeros. The multiplication process involves three nested loops. The outer loop iterates through each row of matrix A, the middle loop goes through each column of matrix B, and the innermost loop computes the dot product of the corresponding row from A and column from B. As we accumulate the product of corresponding elements, we store the sum in the respective position of the result matrix. In the main function, we define two 2x2 matrices and call the matrix multiply function. The resultant matrix product is printed row by row. This operation exemplifies how matrix multiplication combines data from two sources, a fundamental operation in many machine learning algorithms, enabling complex transformations and relationships to be calculated efficiently. Now let's implement the following code that demonstrates how to scale a vector using a transformation matrix. First, we define a function scale matrix, which takes a scale factor as an input. This function returns a 2D scaling matrix, where the scale factor affects both the x and y coordinates by being placed along the diagonal. This effectively enlarges or shrinks the vector based on the provided factor. Next, we create a function called applyTransformation, which accepts a vector and a transformation matrix. This function initializes a result vector to store the scaled values. It performs a nested iteration over the transformation matrix to compute the dot product, multiplying each element of the input vector by the corresponding element in the transformation matrix to obtain the transformed vector. In the main function, we define a vector with specific values, and then we call scale matrix with a scale factor of 2 to generate the scaling matrix. By applying this transformation to our initial vector using the applyTransformation function, we output the scaled vector. This approach exemplifies how linear transformations can be easily implemented in C++, highlighting the practical application of scaling in data normalization for machine learning models. Now let's implement a basic example of calculating eigenvalues and eigenvectors to deepen our understanding of these concepts. The code starts by including necessary headers and defining two functions, simple eigenvalue and simple eigenvector. These functions are designed to take a matrix as input and return a preset list of eigenvalues and eigenvectors, respectively. While the implementation here uses simplified values for demonstration, it serves to illustrate how eigenvalues and eigenvectors might be computed in practice. In the main function, we define a sample 2x2 matrix. This matrix, which might represent a dataset in a more complex application, will be passed to our eigenvalue and eigenvector functions. Once we call these functions, we print the result to the console. This helps visualize the eigenvalues, showing the magnitude of variance in given directions, along with the eigenvectors, which point out the directions of that variance in the data. Such simplifications allow us to focus on understanding the broader concepts involved without delving deep into complex numerical methods that libraries like Eigen or Armadillo provide. This foundational example sets the stage for understanding how we can leverage these mathematical constructs in machine learning techniques such as principal component analysis, PCA, to reduce dimensionality while preserving essential data characteristics. Recap: understanding linear algebra concepts, vectors, matrices, and transformations greatly enhances one's ability to grasp and implement machine learning algorithms effectively. With their mathematical properties, we can manipulate data points, calculate relationships, and facilitate learning processes. Proficiency in these areas allows you to scale datasets and illuminate intrinsic patterns that propel machine learning models forward. So far, we have journeyed through various linear algebra concepts relevant for machine learning, including vectors, matrices, linear transformations, and the importance of eigenvalues and eigenvectors. By grasping these concepts, you're well on your way to harnessing the power of machine learning more effectively. As you continue down this path, remember to apply what you have learned and appreciate the mathematical beauty beneath the models you create. Keep experimenting, coding, and exploring the universe of machine learning. In this lesson, we're diving into solving linear regression tasks using different C++ libraries. This is an exciting and practical application of the concepts we've covered so far. We learned about the foundational concepts of linear algebra that are essential for understanding machine learning algorithms. We explored vectors and matrices, their operations, and how they relate to data representation and manipulation in ML. Additionally, we discussed linear transformations, eigenvalues, and eigenvectors, emphasizing their importance in dimensionality reduction and data scaling. With this knowledge, we are better equipped to apply mathematical concepts to enhance our machine learning models. Now we will cover how to implement linear regression using various libraries like Eigen, Armadillo, and others in C++. Linear regression is a fundamental technique for regression tasks where we're interested in predicting a continuous output based on one or more input variables. The core idea is to fit a line, or a hyperplane in higher dimensions, that best describes the relationship between the input features and the output target. Now let's delve into the implementation of a simple linear regression model using the Eigen library. We start by including the necessary header files, which provide access to the Eigen functionalities for linear algebra operations. In the main function, we begin by generating some sample data. We create a matrix X with dimensions 10 by 2 to hold our input features, including a bias term represented by the first column filled with ones. The second column is populated with sequential values. As we populate the target vector y, we compute it using the equation y equals 2x plus 1 \. This relationship allows us to create a clear dependency between our input features and output targets. After preparing our data, we implement the normal equation method to solve for the coefficients of our linear regression model. This method is implemented in a single line of code, where we calculate the coefficient vector through a series of matrix operations. Lastly, we output the computed coefficients, which represent the slope and intercept of the best fit line for our data. This concise demonstration effectively illustrates the power of the Eigen library in performing linear regression with ease. Now let's implement the following code using the Armadillo library to create a linear regression model. We begin by including the necessary headers for input-output operations and the Armadillo library itself. Within the main function, we first set up our input matrix X and our output vector Y. Here, X has dimensions that accommodate 10 samples and 2 features, initialized to 0. Next, we populate the matrix X with the appropriate values. The first column serves as a bias term filled with ones, while the second column holds the feature values ranging from 1 to 10. Simultaneously, the vector y is populated with corresponding target values generated by a linear relationship, specifically y equals 2x plus 1 /. To compute the linear regression coefficients, we utilize Armadillo's convenient solve method, which efficiently calculates the solution to the linear equation. This approach streamlines the coding process by abstracting complex mathematical computations, allowing us to focus on the overall model structure. Finally, we output the coefficients to the console, providing the fitted slope and intercept that define our linear regression model. Now let's see how we can implement linear regression using MLPAC, a high-level machine learning library that integrates seamlessly with Armadillo for efficient linear algebra operations. In this code, we begin by preparing our dataset with input features and corresponding target outputs. We use Armadillo to create a matrix X filled with random values representing our input features and a row vector Y representing the target variable generated through a linear relationship, specifically y equals 2x plus 1 /. Next, we create an instance of the linear regression class from MLPAC, passing in our matrices X and Y to fit the model. This class simplifies the process of training the regression model, handling the underlying computations for us. Once the model is ready, we can make predictions by calling the predict function on our input features X. The results are stored in the predictions row vector, which we then output to the console. This concise and powerful approach demonstrates how MLPAC makes implementing machine learning models more straightforward and allows us to focus on leveraging our data for predictions. Now let's implement a function to read data from a CSV file using the Eigen library, which is essential for handling real-world datasets. In our code, we create a function called readCSV that takes a file name as input, opening the specified file and setting up a mechanism to read it line by line. Each line is processed to split the data based on commas, converting each string value into a double and storing these values within a row vector. This process continues until all lines are read, resulting in a two-dimensional vector that represents our dataset. Next, we convert this two-dimensional vector into an Eigen matrix using an Eigen map, allowing us to work seamlessly with Eigen's array of linear algebra functionalities. This setup provides a vital bridge between raw CSV data and the structured format required for linear regression analysis. In the main function, we then call our readCSV function to load the dataset into an Eigen matrix. We label the features by selecting all but the last column and assign the target variable as the last column of our loaded matrix. With the data prepared, we proceed to solve for the regression coefficients using the normal equation method, printing the results, which will indicate how our model interprets the relationships within the dataset. Now let's implement the following function to evaluate the performance of our linear regression model using the mean squared error MSE. The mean squared error function takes two parameters, yTrue, which represents the actual target values, and yPred, which holds the predicted values generated by our model. Inside the function, we calculate the squared differences between the true and predicted values, leveraging Eigen's capabilities through the squared norm method. This effectively measures how far off our predictions are from the actual outcomes. Next, in the main function, we define two Eigen vector xd variables to store our actual and predicted values for a straightforward example. We populate yTrue with a series of predetermined true values and yPred with predicted values that approximate these true values but include some small deviations. Finally, we call our mean squared error function using these vectors to compute the MSE. The result is printed to the console, providing a quantitative measure of the model's accuracy. This step is crucial as it offers insights into the model's predictive ability and serves as a foundation for further performance evaluations, such as determining R-squared values and refining our regression approach. Now that we've walked through data loading, regression modeling, and performance evaluation, it's essential to highlight the importance of cross-validation in linear regression. Cross-validation helps ensure that our models generalize well and aren't simply memorizing the training data. We can implement cross-validation by splitting the datasets into training and validation sets, then iteratively training the model and evaluating performance on the validation set. Though implementing k-fold cross-validation in C++ can be a bit involved, it's vital for robust model testing. Lastly, as we wrap up this lesson, we encourage continuous practice and exploration of different datasets and regression challenges. By leveraging libraries like Eigen, Armadillo, and MLpack, you can build robust regression models efficiently. To conclude, remember that linear regression is just the tip of the iceberg in machine learning. Understanding its implementation through various libraries provides a solid groundwork for tackling more complex algorithms in the future. Keep pushing the boundaries of your knowledge, experiment with different datasets, and let the linear regression tasks hone your skills. With persistent practice, you'll soon find yourself comfortably navigating through the world of machine learning, ready to tackle any challenge that comes your way. Now let's dive into parsing data formats, an essential skill in machine learning that allows us to transform raw data into a structured format suitable for modeling. To make great predictions, we must first understand how to manipulate and prepare our data correctly. So far, we learned about solving linear regression tasks using C++ libraries such as Eigen, Armadillo, and MLpack, emphasizing the foundational concepts of linear algebra. We discussed implementing linear regression models and handling real-world datasets, including data preprocessing techniques. Additionally, we highlighted the importance of evaluating model performance using metrics like mean squared error, MSE, and the necessity of cross-validation to ensure models generalize well. Through these lessons, we are building a strong foundation to tackle more complex algorithms in machine learning. Now we will cover parsing different data formats, understanding their structures, and how to utilize them effectively in our machine learning projects. Now let's see how we can implement a simple CSV file reader in C++. In this code, we begin by including necessary libraries for input-output operations and string manipulation. We then define the main function where we open a CSV file named fruits, CSV. Using an ifstream object, we read the file line by line until we reach the end. For each line, we utilize a string stream to facilitate splitting the line at each comma. This allows us to effectively extract individual values, which we store in a temporary vector representing a row of data. As we process each line, we push the row vector into a 2D vector named data, effectively building a two-dimensional representation of the entire dataset. After reading all the lines, we implement a nested loop to iterate through data and print each value, which provides a clear view of the structured content from the CSV file. This method demonstrates a straightforward approach to parsing CSV data, highlighting how to manipulate tabular data in C++. However, it's important to remember that CSV files may not suit more complex data structures, so understanding their limitations is crucial as you progress in data parsing techniques. Next, let's see how we can implement JSON parsing in C++ using the nloman/json library. First, we include the necessary headers for input-output and the JSON library. In the main function, we open a JSON file, in this case, fruits.json, which contains our dataset in a structured format. We create a JSON data object of type nloman, JSON to hold the parsed content of the file. By using the extraction operator, we straightforwardly load the JSON data into our JSON data object. What's particularly useful about JSON is that we can iterate over each item in the JSON array. In our loop for each fruit, we extract its attributes, the name, color, and weight, using the respective keys. This syntax encapsulates the beauty of JSON, allowing easy access to related data. Lastly, we print out each fruit's details to the console in a user-friendly format. This method showcases how JSON parsing in C++ can be flexible and robust, especially for handling complex and nested data structures often encountered in machine learning applications. Now let's see how we can implement XML parsing using the tiny XML2 library in C++. The code begins by including the necessary headers, specifically iostream for input and output operations and tinxml2h, which contains the tiny XML2 functionality for handling XML files. In the main function, we create an instance of tinxml2 XML document. This object will allow us to load and manipulate the XML data. We load the XML file named fruits XML using the load file method, which reads the content of the file into the document object. After loading the file successfully, we access the root element called fruits through first child element. Next, we iterate through each child element fruit using a for loop. Inside this loop, we extract the name, color, and weight of each fruit by navigating to their respective subelements using first child element and calling getText for string retrieval. For the weight, we utilize query int text to convert the text to an integer directly. Finally, the details of each fruit are printed to the console, demonstrating how we can work with hierarchical data structures using tiny XML2. This exercise shows the flexibility and organization that XML provides for data storage and transport. Now let's implement the following code using OpenCV to handle image data, which plays a crucial role in deep learning applications. We start by including necessary headers, such as IOStream for input and output operations, and openc2/openc HPP to access OpenCV functionalities. In the main function, we utilize OpenCV's imread function to load an image file, which in this case is fruit, JPG. It's important to check if the image has been successfully loaded. If not, we output an error message and terminate the program. This step is vital to ensure that subsequent operations only proceed with valid data. If the image loads correctly, we can extract and display its dimensions to understand its size, which is helpful for further processing. Next, we employ the MShow function to show the image in a window titled Fruit, allowing us to visualize the data we are working with. The program concludes with a call to wait key 0, which pauses execution until any key is pressed, ensuring that the displayed image remains visible. Understanding how to manipulate image data is essential for converting these visual inputs into numerical arrays for machine learning models. Now let's implement a simple yet effective data preprocessing function in C++. We will create a function named cleanData, which takes a 2D vector of strings representing our dataset. This function is crucial for preparing our data by removing any empty strings that indicate missing values. By iterating through each row of the dataset, we leverage the std remove algorithm to find and eliminate these empty elements efficiently. As we proceed, we'll also set up a sample dataset in the main function that illustrates various scenarios with some missing entries. This dataset includes fruit names and their respective colors, where we intentionally introduce empty strings to signify missing information. After calling the cleanData function, the code will output the clean dataset, showing only the valid entries. This process emphasizes the importance of data cleaning, ensuring that your model receives high-quality input, which is essential for making accurate predictions. By applying such preprocessing steps, you enhance the reliability of your machine learning tasks and pave the way for better model performance. In conclusion, parsing data formats is an essential skill in the machine learning domain. Whether it is CSV, JSON, XML, or image files, each format has its approach to manipulation. Equipped with the ability to decode and preprocess these formats, we not only enhance our data quality but also set ourselves up for success in building efficient models. As we now wrap up this discussion, remember that understanding your data also means knowing how to work with it in various formats. Mastering these parsing techniques will not only improve your programming skills, but also streamline your machine learning workflows. In the next lesson, we will explore advanced data preprocessing techniques and how to leverage feature engineering to maximize the effectiveness of our models. Stay curious, and let's keep pushing the boundaries of machine learning. In this section, we will explore how to manipulate images using two of the most popular libraries for image processing in C++. Understanding these libraries will give you powerful tools to handle and transform images, an essential skill in computer vision and machine learning applications. So far, we learned about the importance of parsing different data formats in machine learning, focusing on structured formats like CSV, JSON, and XML. We explored how to read and manipulate these formats using C++ libraries, as well as the significance of preprocessing data to remove null values and prepare it for modeling. Additionally, we've discussed handling unstructured formats such as images and the role they play in deep learning applications. Lastly, we emphasize that mastering data manipulation techniques is crucial for effective machine learning practices and set the stage for advancing our data preprocessing skills in future lessons. Now, we will dive into the exciting world of image manipulation and learn to modify, analyze, and process images using C++. Now let's see how we can load and display an image using OpenCV in C++. First, we include the necessary OpenCV and IO header files to access the functions we need. In the main function, we create a CV mat object called image to hold our image data. The imread function is used to load the specified image file into this object. It's important to check if the image loaded successfully. If it didn't, imageEmpty will return true, and we handle this case by printing an error message and terminating the program. Once we have a valid image, we proceed to display it using the MLflow function, which creates a window titled Loaded Image containing our image. The wait key 0 function holds the program execution until a key is pressed, allowing us to view the image before the program exits. This simple yet powerful approach to handling images sets the foundation for more complex operations, such as image manipulation and analysis, which we will explore next. Now that we can load and display images, let's delve into a fundamental operation: resizing. In the following code snippet, we introduce a CV mat object named ResizeImage, which will hold our modified image. We use OpenCV's resize function to transform the original image's dimensions to 300 by 300 pixels, which is particularly useful for standardizing images before they're processed in machine learning applications. Besides specifying fixed dimensions, the function allows for proportional resizing via scale factors fx and phi, giving you flexibility depending on your needs. After resizing, the program displays both the original and resized images in separate windows using MLflow. This not only provides a visual comparison but also enhances your understanding of how the image is altered. Lastly, wait key 0 ensures that the program pauses until a key is pressed, allowing you time to review the results. This resizing process encapsulates essential image manipulation techniques, showcasing the capabilities of OpenCV in transforming image data for further use or analysis. Now let's explore how to convert an image from the BGR color space to grayscale, a common requirement in many image processing tasks. First, we load an image using the imread function, which stores it in a CV mat object called image. It's crucial to check if the image was loaded successfully. If not, we output an error message and terminate the program. Next, we create an empty CV mat object named grayImage to store the resulting grayscale image. We then utilize the CVT_color function, which converts our loaded colored image into grayscale. This function takes 3 arguments: the source image, the destination image, and the color conversion code CV color BGR to gray, indicating that we want to transform a BGR image into a grayscale format. Finally, we display both the original and the newly created grayscale images using the MLflow function, allowing us to visually compare them. By pressing any key, we can close the displayed windows and complete the program, demonstrating how effectively we can manipulate image data with just a few lines of code using OpenCV. Now let's see how we can implement drawing shapes and adding text to an image using OpenCV. In this code snippet, we start by loading an image into a CV mat object. It's crucial to ensure that the image is successfully loaded, hence we check if the matrix is empty and handle the error accordingly. Once we have our image, we can perform various annotations. We begin by drawing a blue rectangle on the image using the rectangle function, specifying the top left and bottom right corners, along with the color in BGR format and thickness. Next, we add a filled red circle at a specific center point, which helps emphasize a particular area in the image. Finally, we utilize the putText function to overlay the text OpenCV on the image, allowing us to highlight the functionality we're demonstrating. We choose the position, font, size, and color for the text to ensure it's prominently displayed. This combination of shapes and text adds valuable visual information to the image, enabling better communication of the data represented. After making these modifications, we display the annotated image in a window, showcasing the results of our work. Now let's implement the following example to apply Gaussian blur to an image. which is a common technique used in image preprocessing. In the code, we start by including the necessary OpenCV headers and define the main function. We use the CV imRead function to read an image from a specified path into a matrix object, CV, mat. It is essential to check if the image was loaded correctly, and if not, we display an error message and terminate the program. Next, we introduce a new matrix, blurred image, to store the blurred output. The core operation is performed using the CV Gaussian blur function, which takes three parameters: the original image, the output matrix, and the size of the Gaussian kernel, specified as 15 by 15 pixels. This function effectively reduces noise and softens the image by averaging the pixel values with the defined kernel, resulting in a smoother image that retains important structural details. Finally, we display both the original and the blurred images using CV imShow, allowing us to visualize the differences and benefits of applying Gaussian blur. The CV wait key 0 command is included to pause the execution until a key is pressed, ensuring we have time to view the results before the program exits. Now let's see how we can implement image thresholding using OpenCV. This technique helps convert a grayscale image into a binary image, which simplifies the image for further analysis and feature extraction. In the code, we begin by loading an image and checking if it's successfully read into a matrix using the imRead function. If the image loading fails, an error message is printed. Next, we convert the original image to grayscale using the CVTColor function, which is essential for thresholding, as it reduces the complexity of the data by focusing only on intensity values. We then apply thresholding with the threshold function, where we define a threshold level at 127. Pixels with values greater than this threshold are set to white, while those below it are assigned a black value. This binary representation can effectively isolate objects in the image based on their intensity. Finally, we display both the original and the resulting binary images using imShow, allowing us to visually assess the effectiveness of the thresholding process. This implementation showcases the simplicity of separating foreground elements from the background in an image, making it a crucial step in image segmentation tasks. Now let's see how we can implement basic image loading using Boost GIL, a versatile library that emphasizes a type-safe approach to image processing. In our code, we begin by including the necessary Boost GIL headers specifically for handling PNG images and accessing all the required functionality. Within the main function, we create a variable img of type RGB8ImageT, which is a representation for an RGB image. Next, we utilize the readImage function to load an image from the specified file path, in this case, a PNG file. The PNG tag indicates the image format being read. Once the image is loaded, we can easily access its dimensions using the width and height methods. These attributes give us important information about the image size, which is crucial for any further processing or manipulation. Finally, we print out the image dimensions to the console, a simple yet effective way to confirm that the image has been successfully loaded. This foundational step paves the way for more advanced image operations in our upcoming lessons. Now let's see how we can implement image conversion in Boost GIL. The code begins by including the necessary Boost GIL headers that enable us to work with different image formats, specifically PNG in this case. Next, we define the main function and declare an RGB image type using RGB8ImageT, which encapsulates our image data. We then employ the readImage function to load a PNG image from a specified path into our RGB image variable. This function automatically handles the format conversion, allowing us to focus on processing the image itself. Once the image is successfully loaded, we prepare to convert it to grayscale. Here, we create a new grayscale image of the same dimensions as the original. Using copy and convert pixels, we efficiently transform each pixel from the RGB format to grayscale without delving into the underlying data structures. This highlights Boost GIL's strength in abstracting pixel operations. Finally, we save our newly created grayscale image back to the disk, demonstrating how straightforward it is to manipulate images across different formats with Boost GIL. This code snippet exemplifies how we can streamline the image processing workflow in C++ while maintaining flexibility and efficiency. Now let's see how we can implement the canny edge detection algorithm using OpenCV. In the code, we start by loading an image from a specified file path into a CV mat object. It's essential to check if the image is successfully opened. If not, we display an error message and exit the program. After ensuring the image is loaded, we convert it to a grayscale format, which simplifies the data and is often a prerequisite for edge detection. Next, we apply the canny function, which is central to this snippet. We provide two threshold values that dictate how the algorithm identifies edges based on intensity gradients. The resulting edge-detected image is stored in the edges matrix. Finally, we use MLflow to display both the original image and the newly created edge-detected image in separate windows, allowing us to visually compare the results. This implementation highlights how edge detection can reveal critical features and boundaries in images, which are crucial in various image analysis tasks. As you can see, the canny edge detector is a powerful tool for extracting meaningful information from visual data. To wrap it all up, image manipulation in C++ can be effectively done using powerful libraries like OpenCV and Boost, GIL. We covered a wide variety of topics from loading images, resizing, color conversions, filtering, drawing shapes, thresholding, and even utilizing image analysis techniques like edge detection. Each technique we've explored equips you with the skills necessary to handle images for computer vision, machine learning, and many other applications. As you continue your journey in mastering image processing, familiarize yourself with the extensive capabilities these libraries offer. The real-world applications are vast, ranging from simple image editing tasks to complex computer vision projects where you can leverage these libraries. Keep experimenting, iterating, and building your skills, and you will be well on your way to becoming proficient in image manipulation with C++. Stay curious and keep pushing the boundaries of your knowledge. Data normalization is a crucial preprocessing step in machine learning. It ensures that different features contribute equally when training models, enhancing their efficiency and performance. In this discussion, we will explore what data normalization is, why it's essential, and the various techniques you can use to normalize your data effectively. So far, we learned about image manipulation using C++ libraries, primarily focusing on OpenCV. We explored essential functions such as loading and displaying images, resizing, color space conversion, drawing shapes, and applying filters like Gaussian blur. Additionally, we discussed image thresholding and analyzed edges using techniques like the canny edge detector. Our journey through these concepts establishes a foundation for developing advanced image processing skills in various applications. Now, we will talk about data normalization and cover several methods including min-max scaling, z-score normalization, and others, emphasizing their importance in machine learning workflows. Now let's implement the min-max scaling technique in C++. In the code, we define a function called min-max scale, which takes a vector of doubles as its input. The first step within this function is to calculate the minimum and maximum values of the vector using the standard library functions std, min element, and std, max element. This is crucial because the min-max normalization relies on these boundary values to rescale the dataset. Next, we create another vector called scaled data to hold the normalized values. A for loop iterates through each element of the original data, applying the min-max scaling formula, subtracting the minimum value and then dividing by the range, which is the difference between the maximum and minimum values. This ensures that all the new values fall within the range of 0 to 1. Finally, in the main function, we demonstrate how to use the min-max scale function by normalizing a vector representing heights. We print the scaled heights to the console, showcasing the transformed values after applying the normalization process. This implementation effectively addresses the potential skew from varying feature scales in machine learning. Now let's see how we can implement z-score normalization in C++. The code begins by including essential libraries such as iostream for input-output operations, vector for handling dynamic arrays, cmath for mathematical functions, and numeric for calculating the mean. The mean function calculates the average of the input data by summing all elements and dividing by the number of elements. Next, the standard deviation function computes the standard deviation by iterating through the dataset, calculating the squared difference from the mean for each value, and then taking the square root of the average of these squared differences. Now let's take a look at the z-score normalize function, which utilizes both the mean and standard deviation functions to normalize the data. It creates a vector to store the normalized values and applies the z-score formula to each element of the input data to compute the normalized z-scores. In main, we define a vector of weights, deliberately including an outlier value to illustrate the impact of z-score normalization. The normalized values are printed to the console, demonstrating how each weight has been transformed, thus allowing for a comparison of values on a standard scale. This implementation highlights the effectiveness of z-score normalization in mitigating the influence of outliers. Now let's implement the robust scaling technique using C++. The first function, quantel, is designed to compute the specified quantel of a given dataset. It does this by sorting the dataset and indexing into the sorted array based on the requested quantel, allowing us to find values like the first or third quantel. Next, we have the robust scale function, which applies the robust scaling transformation. It calls the quantel function to obtain the first and third quantels, Q1 and Q3. Using these quantels, it rescales each data point in the input vector, ensuring that the influence of outliers is minimized. Specifically, each value is recalculated to reflect its position between Q1 and Q3, which improves the robustness of the scaling. In the main function, we demonstrate the usage of robust scale by creating a vector of heights including an outlier. After applying the robust scaling function, the results are printed, showing how the outlier is less influential in the scaled output. This technique is particularly advantageous in datasets where outliers can skew standard normalization methods, thereby making the model more reliable. Now let's see how we can implement one-hot encoding in C++. We begin by including the necessary libraries, iostream, vector, and map. The function one-hot encode is defined to accept a vector of strings representing categories. Inside the function, we create a mapping of each category to an index using a std map, which counts occurrences of each category as we iterate through the input vector. Next, a new vector of vectors, encoded data, is initialized to hold our binary representations. For each category, we create an encoded row vector initialized with zeros, the size of which corresponds to the number of unique categories. We then set the appropriate index in encoded row to 1, indicating the presence of that category for the given input. This encoded row is subsequently added to encoded data. In the main function, we define a sample vector, colors, which includes multiple occurrences of the categories. We invoke the one-hot encode function to transform these colors into their one-hot encoded format. Finally, we print the resulting binary arrays to the console, showcasing how each color is represented, thereby facilitating machine learning algorithms to process categorical data effectively. Finally, it is crucial to remember that normalization should be performed consistently across training, validation, and test sets. When splitting your data into these sets, fit your normalization parameters, such as min, max, mean, or standard deviation, solely on the training data to avoid information leakage. This practice ensures that your model generalizes well on unseen data. In summary, normalizing data is a fundamental step in preparing your dataset for machine learning. Properly normalized data enhances the performance of your machine learning models by ensuring they learn from relevant features and not the scale of the data. Remember to choose the normalization technique suited for your data's characteristics, whether that's min-max scaling, z-score normalization, or robust scaling. As we wrap up this discussion, keep in mind that normalization lays the groundwork for achieving optimal model performance. It allows machine learning algorithms to converge more quickly and accurately while mitigating the risk associated with feature scale disparities. Now, if you have any questions about normalization or want to dive deeper into other preprocessing techniques, feel free to ask. Now let's implement the calculation of the mean squared error (MSE) in C++. This code begins by including the necessary libraries, iostream for input-output operations, vector for using dynamic arrays, and dlib/matrix, H for any advanced matrix operations needed, though not directly used here. We define a function called calculateMSE that accepts two vectors representing the actual and predicted values. The function checks if both vectors are of the same size. If not, it throws an error to ensure that the input is valid. This is crucial for accurate MSE calculation, as mismatched sizes would lead to incorrect results. In the function, a loop iterates through the predictions, calculating the squared differences between each corresponding actual and predicted value. The accumulated squared differences are then averaged to yield the MSE, a smaller number indicating a better fit of the model. In the main function, we initialize two vectors with some sample actual and predicted values and call the calculate MSE function. Finally, we print the resulting MSE. This straightforward approach allows us to easily assess model performance through numerical analysis. Now let's implement the mean absolute error MAE calculation in C++. In this code, we begin by including the necessary headers for input-output operations and to work with vectors and mathematical functions. The calculate ME function is defined to accept two vectors, actual and predicted, representing the true values and the model predictions, respectively. The first step inside this function is to check if both vectors are of equal length. If not, an exception is thrown to prevent further miscalculations. Within the function, we initialize a variable me to store the cumulative absolute error. We then use a loop to iterate through each element of the vectors, calculating the absolute difference between the actual and predicted values and accumulating this into the me. After processing all elements, the final mean absolute error is calculated by dividing the total absolute error by the number of samples, offering a comprehensive average of the errors without bias from their direction. Finally, in the main function, we define sample data for both actual and predicted values, call the calculate me function, and output the result, which demonstrates how effectively the MAE can be utilized to evaluate a model's performance comprehensively. Now let's implement the following C++ code to calculate the R-squared value, a key performance metric for regression models. This function, calculate R-squared, begins by taking two vectors, one for the actual values and another for the predicted values. It checks if these vectors are of the same length, throwing an error if they aren't, ensuring that the calculations are valid. Next, we compute the mean of the actual values, which is essential for determining the total sum of squares. We initialize two variables, sstot and ssres, to accumulate the total sum of squares and the sum of squares of residuals respectively as we iterate through the data. In this loop, we calculate each component. sstot captures the variance of the actual data around its mean, while ssres computes the discrepancy between the actual and predicted values, indicating how well our model fits the data. Finally, the function returns the R-squared value, calculated by subtracting the ratio of ssres to sstot from 1. This implementation not only enables you to understand the strengths of your model, but also provides a quantitative measure of its predictive power in a straightforward manner, readily displayed in the program's output. Now let's see how we can implement the accuracy calculation using a confusion matrix in C++. We start by defining a function called calculateAccuracy, which takes four integer parameters: true positives TP, true negatives TN, false positives FP, and false negatives FN. This function computes accuracy by summing TP and TN, which represents the total number of correct predictions, and divides this by the total number of predictions made, calculated as TP plus TN plus FP plus FN. This division results in a double, ensuring that we maintain precision in our calculations. In the main function, we assume some sample counts for TP, TN, FP, and FN, which might typically come from the results of a classifier after performing predictions on a dataset. After assigning values to these variables, we call the calculateAccuracy function, parsing in our counts. The resulting accuracy is then printed to the console, informing us about the model's performance. This straightforward approach allows us to gain quick insights into how well our classification model is performing based on these key metrics. Now let's implement the metrics for evaluating classification models, precision and recall. We begin by defining two functions, calculate precision and calculate recall, which encapsulate the formulas for these metrics. The calculate precision function takes two parameters, true positives TP and false positives FP. and calculates precision by dividing the number of true positive predictions by the sum of true positives and false positives. This metric helps us gauge the quality of the positive class predictions, highlighting how many of the predicted positives are indeed true. Next, we turn our attention to recall. The calculate recall function also requires two parameters, true positives TP and false negatives FN. Recall is computed as the proportion of true positives out of all actual positive instances, giving us insight into how well our model captures the actual positive cases. In the main function, we define sample values for TP, FP, and FN, then call our precision and recall functions. The results are printed to the console, allowing us to evaluate the model's performance on the positive class effectively. These foundational metrics are essential for understanding the strengths and weaknesses of classification approaches in machine learning. Now let's see how we can implement the F1 score calculation in C++. The function calculate F1 accepts two parameters, precision and recall. A crucial aspect of this function is the check for division by 0. If both precision and recall are 0, it returns an F1 score of 0 to prevent an invalid operation. The F1 score itself is computed as the harmonic mean of precision and recall, giving us a single performance metric that balances the two measures, which is particularly useful in scenarios involving imbalanced datasets. In the main function, we first define some example counts for true positives, TP, false positives FP, and false negatives FN. Using these values, we calculate precision and recall through their respective functions, which compute the proportion of correctly predicted positive instances against the total predicted positives and actual positives. Finally, we compute the F1 score by calling our earlier defined function and print the result. This implementation provides a comprehensive view of the model's predictive capabilities, integrating various performance aspects into a single metric that is essential for evaluating model effectiveness in classification tasks. As we conclude our discussion on performance metrics, it's vital to remember that the choice of metric often depends on the specific goals of your project. For instance, while accuracy may be beneficial in many cases, it can be misleading in scenarios with unbalanced class distributions. Metrics like precision, recall, and F1 score become crucial in such cases, enabling you to assess your model's performance more accurately in real-world applications. With performance metrics in your toolkit, you're now prepared to delve deeper into building robust machine learning models. You'll always need the right tools to assess how they perform, ensuring that your models can make predictions that align with your expectations. That's it for today. Keep exploring and coding. When it comes to building effective machine learning models, having a proper set of hyperparameters is crucial to achieving the desired performance. Today, we will dive into the grid search technique, a powerful method for hyperparameter tuning that can significantly improve your model's results. So far, we learned about the importance of assessing machine learning model performance using various metrics. We explored regression metrics such as mean squared error, mean absolute error, and R-squared, as well as classification metrics including accuracy, precision, recall, and F1 score. Now we will focus on how to select the best hyperparameters for our models, ensuring they perform optimally. To start off, let's clarify what hyperparameters are. Unlike model parameters, which are learned from the training data itself, hyperparameters are configurations that you set before the learning process begins. These parameters can control aspects such as the complexity of the model, the learning rate, and even the number of trees in a forest. Finding the right combination of hyperparameters is essential since they can drastically affect the performance of your model. This is where grid search comes into play. Grid search is a systematic way to work through multiple combinations of hyperparameter values, cross-validating as it goes to determine which combination achieves the best performance. The idea is to define a grid of hyperparameter values and then perform an exhaustive search over this grid to find the optimal parameters. Let's illustrate this with a practical example using a support vector machine, SVM classifier. Now, let's implement the following code to define our hyperparameters and generate combinations based on them. We begin by creating a structure named hyperparameters that encapsulates the kernel type, regularization parameter C, and gamma value. This structured approach helps in organizing these parameters together. Next, we'll write a function called createGrid that generates all the possible combinations of hyperparameters. Inside this function, we initiate a vector to hold the hyperparameter combinations, along with predefined vectors for the kernel types C values and gamma values. Through nested loops, we iterate over each kernel type C value and gamma value, combining them into separate instances of the hyperparameters structure. Each combination is pushed into the grid vector. Upon completing this, the function returns the grid containing all hyperparameter combinations. In the main function, we call createGrid to retrieve this grid and then print out each combination. This systematic generation of parameter combinations lays the groundwork for our upcoming grid search, ensuring we have a comprehensive set of configurations to evaluate against our model. Next, we will implement the evaluation of each hyperparameter combination using k-fold cross-validation. To start, we define a function called cross-validate, which takes a vector of scars and the number of folds. This function calculates the average scar across all folds, thereby giving us a measure of performance for a specific hyperparameter set. Now let's introduce the evaluate model function, which acts as a placeholder for the actual model evaluation logic. In a practical scenario, this would include training the SVM model with the current hyperparameters and validating it on the validation set. For demonstration purposes, it currently returns a random scar, simulating performance evaluation. Following that, we implement the performGridSearch function, which is the heart of our hyperparameter tuning process. This function takes the grid of hyperparameters and the number of folds, iterating over each parameter set. Within a loop, it generates scars for each fold by calling the evaluateModel function and then computes the average scar using cross-validate. Finally, it identifies and prints the best hyperparameter combination based on the highest average scar, ensuring we select the optimal parameters for our SVM model. Now let's implement the following code that demonstrates how to execute a randomized search for hyperparameter tuning. First, we define a function called randomHyperparameters, which randomly selects values for three key hyperparameters: the kernel type, the regularization parameter, C, and the gamma value. This allows for a more flexible exploration of the hyperparameter space compared to grid search. Next, we have the performRandomizedSearch function, where we specify the number of iterations to run the search and the number of folds for cross-validation. Inside this function, we initialize variables to keep track of the best scar and the corresponding hyperparameters. For each iteration, we generate a new set of random hyperparameters, evaluate the model using k-fold cross-validation, and update our best parameters if the current configuration yields a higher average scar. Finally, we use the main function to set up the randomness seed, specify the number of iterations and folds, and call the performRandomizedSearch. This structure not only facilitates efficient exploration of hyperparameter combinations, but also exemplifies a practical use of randomized search in machine learning model optimization. Regardless of whether you choose grid search, randomized search, or a more advanced technique like Bayesian optimization, remember that the ultimate goal is to enhance your machine learning model's predictive power. Selecting the right hyperparameters can mean the difference between a mediocre model and one that performs truly well in real-world applications. Moreover, it's a common practice not to rely solely on one evaluation metric. Depending on the nature of your specific problem, be it classification, regression, or a hybrid, you should consider multiple metrics, allowing you to form a comprehensive view of your model's performance during the selection process. As we wrap up our exploration of hyperparameter tuning and grid search, let's reinforce the key takeaways. Proper hyperparameter tuning is critical to building models that not only learn effectively, but can also generalize well to new data. We established how to set up grid search, generate hyperparameter combinations, evaluate them using cross-validation, and even touched on randomized search as an alternative when dealing with extensive search spaces. Remember, hyperparameter tuning can be a time-consuming process, but the performance improvements it yields can be invaluable. So get excited about optimizing your models. After all, improving their performance might just lead to that breakthrough in your machine learning projects. Keep experimenting and don't shy away from pushing the limits. Success often lies just beyond the boundaries of what seems feasible. Happy coding. Clustering is an unsupervised machine learning method that's essential for data analysis. It allows us to split an original dataset of objects into groups classified by their properties. This formation of groups or clusters happens without any specific training or labeled data. Instead, it operates based on the intrinsic properties of the data, uncovering patterns that might not be readily apparent. So far, we learned about the critical role of hyperparameters in machine learning model performance and the grid search technique for hyperparameter tuning. We discussed the importance of assessing models using various metrics and how to generate combinations of hyperparameters for a support vector machine, SVM. We also explored the process of evaluating these combinations through k-fold cross-validation and introduced randomized search as a more efficient alternative. Overall, effective hyperparameter tuning is essential for enhancing model performance and generalization. Now, we will dive into the fascinating world of clustering, examining its principles, methods, and practical applications. Let us explore the implementation of the Euclidean distance function in C++. This function is designed to calculate the straight-line distance between 2 points in a two-dimensional space, which is fundamental for clustering algorithms that depend on this metric to group data points. We start by including the CMath library, which supplies the necessary mathematical functions for our calculations. The Euclidean distance function accepts 4 parameters: the x and y coordinates of 2 points designated as \x1 y1 \, and \x2 y2 \. Within the function, we utilize the sqrt function to compute the square root of the sum of the squared differences between the respective coordinates. Specifically, we subtract \x1 from \x2 square the resulting value and apply the same method to the y coordinates. This approach succinctly embodies the formula we previously reviewed. Following this, we will test the function by calling it with different sets of coordinate pairs. This will enable us to calculate distances within our dataset, which is vital for conducting clustering analysis. By effectively leveraging this distance metric, we can gain deeper insights into the relationships between points in feature space, ultimately improving the performance of our clustering algorithms as we progress. We will now implement the Manhattan distance function using C++. This method is designed to calculate the distance between 2 points in a grid-based manner, making it especially useful in clustering contexts where minimizing the influence of outliers is important. The Manhattan distance function requires 4 parameters that represent the coordinates of 2 points: \x1 y1 and \x2 y2 \. Within the function, we employ the fabs function to ensure that we accurately take the absolute values of the differences between the respective coordinates. By adding these absolute differences together, we can determine the Manhattan distance. After establishing the formula, we can convert it into code. The key line in the function calculates \x2 x1 plus y2 y1 \, which indicates the total distance between the 2 points in a rectangular grid setup. When this function is successfully invoked with specific point coordinates, it will yield a numerical value that represents the distance between them. This implementation is highly beneficial for clustering algorithms that utilize Manhattan distance as a similarity measure among data points. By adopting this method, we can significantly enhance the robustness of the clustering analysis, particularly when the data is susceptible to outliers. Now let's see how we can implement the k-means algorithm in C++ using the MLpack library. The function k-means takes 3 parameters: a matrix of input data, the number of clusters defined by numClusters, and a row vector called assignments, which will store the cluster assignments for each input data point. Within the function, we first create an instance of the k-means class from the MLpack library. This object provides us with methods to perform the clustering operation. We then invoke the cluster method on our k-means object, passing the input data, the number of clusters, and the assignments vector. This method executes the k-means clustering process, assigning each data point to the nearest centroid and updating the centroids iteratively until convergence. The result is that the assignments vector now holds the cluster ID for each data point, allowing us to see how the data has been categorized. This straightforward implementation captures the essence of the k-means algorithm, enabling efficient clustering of data based on proximity to centroid locations. Now let's implement the DBSCAN clustering algorithm using the MLpack library in C++. First, we initialize a DBSCAN object, specifying the necessary parameters for the clustering process, epsilon and min_pts. The epsilon parameter defines the maximum distance between 2 points to consider them as neighbors, which is crucial for determining the density region. Meanwhile, min_pts sets the minimum number of points required to form a dense area, thereby helping to distinguish between car points, border points, and noise in the dataset. Next, we declare a row size t variable named assignments that will hold the cluster identifiers for our input data points after clustering. Once our DBSCAN object is instantiated with the specified parameters, we then call the cluster method on our DBSCAN object. This method takes our input dataset and populates the assignments variable with the corresponding cluster IDs for each data point. The ability to identify and group points based on density makes DBSCAN particularly effective for detecting noise and outliers, enhancing our understanding of the dataset's structure. Next, we will implement the mean-shift clustering algorithm in C++. This algorithm is unique as it does not require us to predefine the number of clusters, allowing it to adaptively identify the appropriate groupings based on data density. To start, we create an instance of the mean_shift class. We then use the estimateRadius function, which analyzes the distribution of input data points and suggests an optimal radius for cluster formation. This is crucial since the algorithm relies on understanding the local density of points. After determining the radius, we set it for our mean_shift object with the radius method. This sets the range over which the algorithm will search for high-density areas. We prepare to store the results of our clustering by declaring an assignments array, which will hold cluster identifiers for each input point, and a centroids matrix to record the center of each detected cluster. Finally, we invoke the cluster method, which performs the actual clustering process and fills our assignments and centroid structures with the results. This allows us to analyze the clusters formed based on the input data, uncovering the underlying patterns effectively. Now let's take a look at how we can visualize the results of our clustering algorithm using C++. The first step in the code involves creating a container, plot clusters, which is a data structure designed to hold the points belonging to different clusters. We iterate through each data point in our input dataset, using a loop that runs from 0 to the number of columns in the input matrix, which represents our feature space. Within this loop, we retrieve the cluster index assigned to each data point. Using this index, we organize the points into their respective clusters by pushing the coordinates of the points into pairs stored in plot clusters. This effectively groups the x and y coordinates of each data point according to which cluster it belongs to, allowing us to visualize the spatial distribution of the clusters. Finally, to create a visual representation of our clustering results, we call the plot clusters function, parsing in our organized clusters, a title for the plot, and a file name indicating where to save the resulting visualization. This ensures we can easily analyze how well our clustering performed and gain insights into the data's underlying structure. Now let's briefly summarize and discuss some of the real-world applications of clustering. From customer segmentation in marketing to classifying wildlife and even detecting fraud in finance, clustering is a versatile tool in machine learning. It enables businesses to draw insights about their customers or data and act accordingly, thus leveraging data-driven decisions. For instance, in customer segmentation, businesses can use clustering to categorize customers based on behavior or purchase history, allowing for targeted marketing strategies. Similarly, clustering can be applied in medical diagnosis to group patients with similar symptoms or health records to tailor treatments more effectively. In conclusion, clustering is an essential unsupervised learning technique that provides a means for identifying underlying patterns in complex datasets. The various algorithms, k-means, DBSCAN, mean-shift, each have their strengths and ideal use cases, allowing practitioners to choose the most appropriate method based on their specific datasets and goals. With solid distance metrics, efficient algorithms, and powerful visualization tools, the potential for clustering in data analysis is vast, and understanding its intricacies will surely enhance your data science prowess. Clustering algorithms are vital tools in data analysis, allowing us to group similar data points in meaningful ways. Today, we will dive deep into the various types of clustering algorithms, mapping their uses across numerous industries and scenarios. So far, we've learned about clustering as an unsupervised machine learning method for grouping data based on similarity, utilizing distance metrics such as Euclidean and Manhattan. We introduced popular clustering algorithms including k-means, dbSCAN, and mean shift, each suitable for different data structures and cluster shapes. We also emphasized the importance of visualizing clustering results to gain insights into the data. Overall, clustering provides valuable applications in various fields, from marketing to healthcare, facilitating data-driven decision-making. Now we'll explore the specific types of clustering algorithms, how each operates, and their practical applications. Next, we will implement the k-means clustering algorithm in C++. Let's take a closer look at the code that facilitates this process. The function k-means clustering takes three parameters: a constant reference to the dataset data, the number of clusters k, and a reference to a row vector assignments that will store the resulting cluster assignments for each data point. Within the function, we first create an instance of the k-means object from the MLpack library, allowing us to utilize its built-in cluster functions. After that, we call the cluster method on this object, passing in our dataset the number of clusters and the assignments vector. This method handles the internal workings of the k-means algorithm, including the assignment of data points to the nearest centroids and the recalculation of those centroids iteratively. Once the clustering is complete, the assignments vector will contain the indices of the clusters that each data point belongs to, providing a straightforward representation of the clustering results. This implementation showcases how easily we can leverage existing libraries in C++ to apply powerful machine learning techniques like k-means clustering. Now let's see how we can implement the dbSCAN algorithm in C++. This code begins by including the necessary header file from the MLpack library for dbSCAN functionality. The function dbSCAN clustering is defined, taking in four parameters: the dataset as a matrix, the epsilon value which dictates the maximum distance for defining neighborhoods, the min-PTS threshold representing the minimum number of points required to form a dense region, and a row vector for storing cluster assignments. Inside the function, we create an instance of the dbSCAN class by passing the epsilon and min-PTS parameters. This initializes the clustering object with the specified configuration. The key part of this implementation is the cluster method, which takes our data and the assignments variable. This method executes the clustering process, grouping the data points based on density. Once the clustering is completed, the assignments variable will contain the cluster indices for each point, with outliers indicated by distinct identifiers. This succinct implementation highlights dbSCAN's strength in handling variations in density and identifying outliers effectively, making it particularly valuable for complex, real-world datasets. Next, we will implement the mean shift clustering algorithm, which allows us to discover clusters without predefining the number of groups. To begin, we include the necessary header file from the MLpack library, which provides us with the tools to utilize the mean shift algorithm. Now let's see how we can write the function for mean shift clustering. The function mean shift clustering takes in two parameters: data, a matrix containing our dataset, and assignments, a row vector that will store the cluster assignments for each element in the dataset. Inside the function, we create an instance of the mean shift class, which encapsulates the functionality of the algorithm. We then invoke the cluster method on our mean shift object, passing in the data, matrix, and assignments vector. This call executes the mean shift algorithm, processing the data to identify clusters based on density. The results will be neatly stored in the assignments vector, indicating which cluster each data point belongs to. This straightforward implementation demonstrates how mean shift can effectively analyze complex datasets without prior knowledge of the underlying cluster structure. Next, we will write the following code to implement the hierarchical clustering technique using the MLpack library in C++. This code begins by including the necessary header file for hierarchical clustering, ensuring we have access to the required functionality. In the function hierarchical clustering, we accept three parameters: the input data in the form of an armadillo matrix, the number of clusters we wish to create, and a row vector to store the cluster assignments. Inside the function, we instantiate an object of the hierarchical clustering class from the MLpack library. This object is responsible for carrying out the clustering process. By invoking the compute method on this object, we initiate the clustering operation, where the method takes the dataset, the variable for cluster assignments, and the desired number of clusters as arguments. Once executed, the compute method clusters the data points into the specified number of groups, which are then reflected in the assignments variable. This highlights not only the process of forming clusters, but also the utility of hierarchical clustering in generating insights through its dendrogram representation. Now that we have seen a variety of algorithms, let's shift gears and discuss applications. Clustering plays a crucial role across many industries, such as marketing, where companies use clustering for customer segmentation. By identifying groups of similar consumers based on purchasing habits or preferences, businesses can tailor marketing strategies that resonate with each segment, ultimately increasing engagement and sales. In the healthcare industry, clustering functions in various capacities, from classifying patients with similar symptoms to developing efficient treatment plans. It allows medical providers to categorize patient data, revealing patterns that can result in improved patient outcomes. For instance, if a hospital notices a cluster of patients exhibiting similar reactions to a treatment, they can direct their efforts towards understanding and optimizing that treatment modality. Moreover, in finance, clustering algorithms are particularly adept at fraud detection. Financial institutions can utilize clustering to identify unusual transaction patterns that deviate from the norm. For example, if a cluster contains transactions that occur in rapid succession outside the typical customer behavior pattern, those transactions may warrant further investigation. This proactive approach is crucial for combating fraudulent activities and maintaining customer trust. Moving on to retail, clustering analyzes product purchase behavior, helping in inventory management, product placement, and enhancing customer experience. Retailers can discover buying trends and adjust their offerings accordingly. For instance, if clustering shows that certain products often sell together, businesses can implement bundling strategies to increase sales. In the realm of social media and content recommendation, clustering algorithms help curate content specific to user interests by analyzing user behavior patterns and groupings. Users with similar content consumption habits can be clustered together, allowing platforms to recommend new content likely to catch their attention. By analyzing interactions, features, and preferences, clustering significantly enhances user engagement metrics. As we've navigated through the various clustering algorithms and their applications, it is essential to emphasize the value of visualizing our clustering outputs. Visualization not only provides immediate insights into the data, but also enhances our understanding of how well the clustering algorithm has performed. Effective visualization techniques can range from simple scatter plots to advanced 3D representations, depending on the complexity and dimensionality of the dataset being analyzed. Finally, it's essential to understand that no single clustering algorithm is superior in all situations. Each algorithm comes with its strengths and weaknesses, and selecting the appropriate method depends largely on the nature of the dataset and the specific requirements of the application. Factors such as the size of the dataset, the presence of noise, and the desired cluster shape should guide your choice. Clustering is an immensely powerful technique that serves as a foundational stone in the broader landscape of machine learning. With the ability to discern patterns, group data, and reveal insights, it remains an indispensable tool across various industries and applications. As you proceed on your data science journey, mastering these clustering algorithms will contribute significantly to your analytical toolkit. So as we wrap up today's lesson on types of clustering algorithms, the takeaway is simple. Understanding and leveraging the right algorithm can unlock doors to profound insights within your data. Whether you are in marketing, healthcare, finance, or any other field, the applications of clustering algorithms are vast and impactful. Keep experimenting with different clustering methods, visualize those outcomes, and let the data lead you to the stories it holds. Thank you for joining me today, and I look forward to continuing this journey into the world of data analysis together. Anomaly detection is a crucial component of data analysis, where we focus on identifying unexpected values within a dataset. An anomaly, in simple terms, refers to any deviation in system behavior or data value from what is considered standard or expected. These anomalies can take on various names, such as outliers, errors, deviations, or exceptions, but their core essence remains the same. They signify something unusual that merits investigation. So far, we learned that clustering algorithms are essential for grouping similar data points within datasets, and that various types, such as k-means, dbSCAN, and mean shift, serve different purposes based on data structure and characteristics. We also covered hierarchical clustering and its two main types, emphasizing its dendrogram representation. Clustering has wide-ranging applications across industries, including marketing, healthcare, finance, and social media, enhancing data-driven decision-making. Finally, it's important to visualize clustering results and choose the appropriate algorithm based on the specific dataset needs for effective analysis. Now we will delve into the fascinating world of anomaly detection, exploring various methods, applications, and practical implementations. Anomaly detection can be thought of as a detective work within the data realm, searching for those peculiar data points that simply don't fit in. In many industries, detecting anomalies can be indicative of fraud, security breaches, mechanical failures, or even unusual customer behavior. For instance, in financial sectors, an unusual spike in transaction activity might suggest fraudulent behavior. Therefore, having robust anomaly detection mechanisms in place is fundamental to ensuring operational integrity. Now let's implement the following C++ code to apply the z-score method for anomaly detection. The code begins by including essential libraries and then defines two helper functions. The first function calculates the mean of a dataset using the accumulate function, which effectively sums all elements and divides by the number of elements. The second function computes the standard deviation by iterating through the dataset, accumulating the squared differences from the mean, and taking the square root of their average. Next, we define the main function detect anomalies, where the detection logic occurs. After calculating the mean and standard deviation using the earlier functions, we iterate through the data again to compute the z-score for each data point. If the absolute value of the z-score exceeds a threshold of 3, it indicates a significant deviation from the mean, prompting us to consider that point as an anomaly, which is then added to a results vector. Lastly, we have a main function, which initializes a sample dataset containing an identifiable anomaly. It calls the anomaly detection function and displays the detected anomalies on the console, thereby providing a complete approach to applying the z-score technique effectively. Now let's see how we can implement a simplified version of the isolation forest algorithm in C++. The code defines a class called isolation forest that encapsulates the methods for fitting the model to a dataset and predicting anomalies based on a specified threshold. The fit method takes a vector of data points and creates a random sample to simulate the isolation process. Here, we employ random shuffling and restrict the sample size to 256, allowing for a simple yet effective demonstration of the algorithm. Next, the predict method calculates anomaly scores for each data point in the dataset. For each point, it calls the isolated score method, which provides a basic assessment based on whether the point exceeds a predefined threshold value of 20. This scoring mechanism is quite naive and serves only for demonstration purposes, focusing the main concept of isolation forest, isolating more anomalous points with fewer splits. Finally, in the main function, we create an instance of the isolation forest, fit it with sample data, and then obtain and print the anomaly scores, providing a hands-on understanding of detecting anomalies using this method. Next, we will implement the dbSCAN algorithm, which is particularly effective in identifying anomalies based on the density of data points. The dbSCAN class begins with a constructor that accepts two parameters, EPS, the maximum distance for points to be considered as neighbors, and min-PTS, the minimum number of points required to form a dense region. Now let's see how we can fit our model using the fit method. Inside this method, we initialize two unordered sets, visited to track the indices of data points we have already examined, and anomalies to store the indices of points classified as anomalies. As we iterate through each data point, we first check if it has been visited. If not, we add it to the visited set and perform a region query to find its neighbors. Next, if the number of neighbors is less than min PTS, we classify the point as an anomaly. Otherwise, we would typically expand the cluster, though this example keeps it basic. Finally, we print out all detected anomalies, showcasing points identified as being in sparse regions. Through this implementation, students can grasp how DBSCAN functions to dynamically identify points that stand out from dense clusters, aligning perfectly with our anomaly detection theme. Anomaly detection presents a broad spectrum of techniques and methodologies, suitable for various types of data and different applications. As we've explored today, statistical approaches like Z-score, advanced methods such as isolation forest, and clustering techniques like DBSCAN can unravel data irregularities. Going forward, applications of anomaly detection in real-world scenarios are vast. In cybersecurity, anomaly detection systems monitor network traffic for unusual patterns that could signify intrusion activities. In industrial settings, they can alert systems to machine malfunctions before they lead to costly breakdowns. In finance, as highlighted earlier, they play a pivotal role in fraud detection, safeguarding businesses and consumers alike. Whether you're hoping to enhance your data insights, detect fraud, or ensure system reliability, understanding anomaly detection opens the door to more efficient data management and insight-driven decisions. As you embark on implementing these techniques, remember that the choice of method should align not only with the dataset characteristics, but also with the specific objectives of your analysis. Happy coding, and may your detection algorithms uncover all those hidden anomalies waiting to be found. Anomaly detection is a pivotal tool in today's data-driven world, where identifying unexpected data points can make all the difference in various applications. In this lesson, we will dive into the various learning approaches we can adopt for anomaly detection, showcasing popular methods along the way. So far, we learned about anomaly detection's significance in identifying unexpected values and behaviors in datasets. We explored methods like the Z-score, isolation forest, and density-based approaches such as DBSCAN. Now we will cover various learning-based techniques for detecting anomalies, emphasizing their implementations and practical uses. Let's unravel these fascinating methods together. Now let's see how we can implement a simple support vector machine (SVM) in C++. The SVM class begins with a method called fit, which takes in a vector of training data represented as pairs of coordinates. While the actual logic for model training is simplified in this example, it acknowledges the training dataset and indicates that the model is prepared for future predictions. Next, the predict method is designed to classify new data points based on a naive linear decision boundary. Here we establish a hypothetical threshold value of 5. If the sum of a data point's x and y coordinates exceeds this threshold, the point is classified as normal, otherwise it is labeled as anomaly. This basic classification method serves as an introductory demonstration of how SVM operates in distinguishing between normal and anomalous data. Finally, in the main function, we create an instance of the SVM class and define a simple dataset of coordinate pairs. After training the model with this data, we classify a new point, showcasing how the SVM can predict whether this unseen point falls within the normal range or is considered an outlier. This establishes a foundational understanding of SVMs in anomaly detection contexts. Now let's see how we can implement the k-means algorithm for clustering. The k-means class begins by defining the constructor, which accepts the number of desired clusters, denoted as k. The fit method is where the clustering takes place, starting by initializing the centroids using the first k points from the input dataset. Next, we enter a loop that continues until no changes occur in centroid positions. Inside the loop, we assign each data point to the closest centroid using the find closest centroid function, which calculates the Euclidean distance between the data point and each centroid to identify the nearest one. Once all points are assigned, we update centroids by computing the mean of all points in each cluster through the compute centroid method. If any centroids change, the loop will run again to reassign points and update centroid positions until convergence is achieved. After this iterative process completes, the algorithm prints a completion message, indicating that clustering has been successfully finished. This approach is beneficial for identifying anomalies, as points that remain unassigned or belong to small clusters can be flagged as outliers, allowing us to detect unusual patterns in the data effectively. Now let's see how we can implement the oneClass SVM in C++. This code defines a class named oneClass SVM which has two main methods, fit and predict. The fit method accepts a vector of training data, which in this case consists of pairs of double values representing coordinates. When this method is called, it stores the training data and prints a message indicating that the model has been trained. Next, we have the predict method, which takes a single point as input and determines whether it is classified as normal or anomaly. The logic implemented here uses a simple threshold boundary set at 5 for both coordinates. If the point's coordinates are below this boundary, the method returns normal, otherwise it classifies the point as an anomaly. This simplistic approach serves to illustrate the concept of oneClass SVM, focusing on how it operates by learning from the majority class instead of relying on labeled data. Finally, in the main function, we create an instance of the oneClass SVM, fit it with some sample data, and test it with a new point. The output will showcase whether this point is classified as normal or an anomaly based on the learned boundary. Now let's implement a simple autoencoder in C++. The autoencoder class begins with a method called fit, which accepts a vector of vectors containing training data. In this method, we store the provided data into a class member and print a message confirming that the autoencoder has been trained. This simulates the training process, where in a real implementation, you typically incorporate a more sophisticated algorithm to learn data patterns. Next, we introduce the reconstruct method, which takes an input vector and calculates a reconstruction error. This method iterates through the input data, comparing each element with a corresponding representative from the training data to compute the squared differences, which contribute to the total reconstruction error. The underlying idea is that normal data will minimize this error, whereas anomalies will produce a significantly larger error, signaling their divergence from expected patterns. In the main function, we instantiate the autoencoder class and create a sample dataset for training. After fitting the model to the training data, we evaluate it using a new input point, here, a value that clearly diverges from the normal data. Finally, we output the calculated reconstruction error, which in this context serves as an indicator of potential anomalies based on how well the new data point fits the learned representation. Now that we've navigated through the various learning approaches to anomaly detection, it's clear that different techniques cater to different situations and datasets. Each method has its own strengths and application areas, from supervised techniques like SVMs to unsupervised clustering approaches like k-means and oneClass SVMs, and finally to semi-supervised autoencoders. The world of anomaly detection is rich and varied. Choose the method that aligns best with your dataset's nature and the desired outcomes of your analysis. Each technique informs decision-making, operational reliability, and ultimately the integrity of your systems. The flexibility and adaptability of these approaches make them invaluable tools in the ever-evolving landscape of data science. With this knowledge at your fingertips, you can confidently implement anomaly detection methods that suit your needs. As we wrap up this lesson, it's essential to recognize the importance of continuous learning and practice in refining your understanding of these methodologies. Experiment, explore, and find what approaches work best for your specific use cases. Happy coding, and may your data journeys be filled with insightful discoveries. The main goal of dimension reduction methods is to simplify complex data by transforming it into a lower dimensional space while still preserving essential information. Imagine diving into a massive sea of data points with countless dimensions. It can be quite overwhelming. Dimension reduction methods come into play to help navigate through this complexity, making it easier to visualize, interpret, and analyze the data. So far, we learned about the significance of anomaly detection and various approaches used to identify unexpected data points. We explored supervised learning techniques like support vector machines, SVM, and unsupervised methods such as k-means clustering and one-class SVM. Additionally, we touched on semi-supervised learning with autoencoders, highlighting their role in detecting anomalies based on reconstruction errors. Each technique has distinct strengths, making them suitable for different types of datasets and analysis goals. Now we will cover the various dimension reduction methods, specifically focusing on their categories, advantages, and implementations in C++. First, let's begin with the fundamental understanding of dimensionality reduction. Essentially, the dimension of the transformed representation should correspond with the internal dimension of the data. What this means is that we should aim for a new representation that captures the significant attributes of our original data within fewer dimensions. Think of it like turning a complicated jigsaw puzzle into a simplified version while still showing the main picture, without losing critical details. Dimensionality reduction can help mitigate the issues posed by the curse of dimensionality, where having too many features may create data sparsity, complicating model performance. This reduction serves multiple purposes, such as improving classification efficiency, aiding visualization, and easing the interpretation of analytical results. A common note here is that dimension reduction should only be applied when specific data points are redundant. Otherwise, you risk discarding important information. One common approach to reducing dimensions is through feature elimination, which targets non-informative features that introduce noise into our model, thus impacting estimation accuracy. Correlated features that offer duplicate information can also create distortion in the model's results, necessitating a more streamlined approach to analyze the data effectively. Now let's see how we can implement principal component analysis, PCA, in C++. We begin by including the necessary eigen and standard libraries to handle matrix operations and input-output functionalities, which are essential for our PCA implementation. The PCA function takes two parameters: an input dataset represented as a matrix and the target dimension to which we want to reduce our data. The first step inside the function is to center the data by subtracting the mean of each column from the respective elements. This is crucial as it ensures that the PCA transformation will focus on variance rather than location in the space. Subsequently, we compute the covariance matrix, which captures how the data dimensions vary together. This is done by multiplying the transposed centered data matrix by the centered data itself, and normalizing it based on the number of samples minus 1. Next, we utilize the self-adjoint eigensolver from the eigen library to compute the eigenvalues and eigenvectors of the covariance matrix. The eigenvectors corresponding to the largest eigenvalues reveal the directions of maximum variance in the data. By selecting only the top eigenvectors determined by the target dim, we effectively retain the most informative features. Finally, we project the centered data onto this new feature space, outputting the reduced data matrix for analysis or further use, demonstrating PCA's efficacy in dimensionality reduction. Next, we will write the following function to perform singular value decomposition, SVD, for dimensionality reduction. This implementation begins with including the necessary eigenheaders for matrix operations, ensuring we have the functionality to manipulate and decompose matrices effectively. Within the SVD reduction function, we pass an input matrix data along with the desired dimensionality target dim. The core of this function utilizes the BDCSVD class from eigen, which efficiently computes the SVD of a given matrix. This decomposition results in three matrices, U, S, and V, encapsulating the fundamental structure of the data. We specifically focus on the U matrix, which contains the left singular vectors. By taking the top rows corresponding to the target dimension, we effectively reduce the dimensionality while retaining the most significant features of our dataset. This step is pivotal as it encapsulates the principal directions in which the variance of the data lies, facilitating simpler and more interpretable analysis. Finally, we print the reduced matrix to observe the outcomes of our dimensionality reduction process, showcasing the condensed representation of the initial data. This powerful method is crucial in datasets where interpretability and simplicity are paramount. Next, we will write an example implementation of independent component analysis, ICA, using a fictive library named Libica. This code demonstrates how we can extract independent components from mixed data, which is crucial in applications like blind source separation. First, we include the necessary headers for input-output operations and the ICA library. The function ICA example takes two parameters: data, which represents our input dataset in an eigenmatrix format, and numComponents, indicating the number of independent components we want to extract. Within this function, we define an eigenmatrix called components to store the results of our ICA operation. We then call the hypothetical function performICA, which processes the input data, filling the components matrix with the extracted independent components. Finally, the code outputs the independent components directly to the console so that we can visualize the results. This method highlights ICA's focus on discovering statistically independent sources within the data, distinguishing it from other dimensionality reduction techniques like PCA, which aims for uncorrelated components. Now let's implement the following C++ code for T-distributed stochastic neighbor embedding TSNE, a powerful technique for visualizing high-dimensional data. In this implementation, we start by including the necessary headers, namely the standard input-output library and a placeholder for the TSNE library. The function TSNE reduction accepts a matrix of type eigen, matrix XD representing our data, and an integer targetDim that specifies the number of dimensions we want to reduce our data to. Within the function, we declare a matrix named reduceData to store the output of the TSNE transformation. The essential step occurs when we call a hypothetical function, performTSNE, which presumably handles the intricacies of TSNE processing, transforming our original data into the reduced representation while preserving the relationships among points. Finally, we display the reduced data using standard output. This implementation showcases how straightforward it can be to perform complex dimensionality reduction tasks using the right libraries and well-defined functions. Now let's implement the following code to create an autoencoder, which will help us achieve dimensionality reduction through learned representations. First, we include the necessary libraries and define our function autoencoder example, which takes in an eigen, matrix XD data object representing our dataset, and an integer, compressedDim, for the dimensions we wish to reduce our data to. Within this function, we initiate an autoencoder instance, passing in the number of input features from our dataset along with the desired compressed dimensions. This sets up the model to learn the important features in our data. Next, we train our autoencoder using the provided dataset, allowing it to adjust its internal parameters to effectively learn the representations of the data. After training, we invoke the encode method on our autoencoder instance, passing the original data. This method compresses our data into the lower dimensional representation. Finally, we print the reduced data to the console. This process highlights how autoencoders can learn complex mappings from high-dimensional inputs to much simpler representations, revealing the essential underlying structures in the data while minimizing loss of information. As we wrap this up, dimensionality reduction methods stand as an essential tool in machine learning, transforming high-dimensional data into lower-dimensional forms while retaining insightful attributes. Each approach has its own strengths and weaknesses, making them suitable for specific scenarios. By applying these methods competently, you can enhance model performance and create compelling visualizations of your data. Keep exploring various techniques, try implementing them out, and customize the codes as per your dataset's needs. In the long run, a solid understanding of dimensionality reduction will undoubtedly advance your data science skills. To reduce the dimension of our data efficiently, we have to analyze its structure and find the top axes of an ellipsoid that represents our data distribution. The objective is to go from a space with a high number of dimensions to a more manageable number while retaining essential characteristics. So far, we learned about the importance of dimension reduction methods in simplifying complex data while maintaining key information. We discussed various techniques like principal component analysis, PCA, singular value decomposition, SVD, independent component analysis, ICA, T-distributed stochastic neighbor embedding, TSNE, and autoencoders, each with unique characteristics and applications. These methods assist in navigating the challenges posed by high-dimensional data, enhancing visualization, interpretation, and model performance. As we proceed, we'll delve deeper into exploring linear methods for dimensionality reduction, such as PCA and SVD, highlighting their applications and how to implement them in C++. Now let's implement the function to compute the covariance matrix, which is essential for PCA. Our function, compute covariance, takes a matrix of data as input and first centers it by subtracting the mean of each column from the corresponding entries in the data rows. This centering ensures that our data is correctly aligned around the origin, which is a crucial step before calculating the covariance. Once the data is centered, we proceed to compute the covariance matrix by taking the outer product of the centered data. This operation tells us how the variables in our dataset vary together, which is vital information for understanding the structure of the data. Finally, we normalize the covariance matrix by dividing it by the number of data points minus 1, providing us a reliable metric of variance among the dimensions. This matrix will subsequently be used in the eigenvalue decomposition to identify the principal components that maximize variance, forming the foundation for our dimensionality reduction process in PCA. Now, let's see how we can implement the PCA function to perform our dimensionality reduction. We start by calculating the covariance matrix of the input dataset, which captures how different dimensions in our data relate to each other. This is done using the compute covariance function we've defined earlier. Next, we utilize Eigen's self-adjoint eigensolver, a powerful tool for computing the eigenvalues and eigenvectors of our covariance matrix. The eigenvalues inform us about the variance explained by each principal component, while the eigenvectors represent the new axes we'll project our data onto. Subsequently, we create a sorted list that pairs each eigenvalue with its corresponding eigenvector, allowing us to rank these components by the variance they capture. With this information, we select the top k eigenvectors, where k is determined by our target dimensionality, ensuring that we retain the most significant features in our reduced dataset. Finally, we project the original data onto the new reduced space defined by the selected eigenvectors, producing a lower dimensional representation of the data that maintains its essential characteristics. The resulting reduced data is then printed for review, showcasing the effectiveness of PCA in simplifying our dataset while preserving important information. Now let's see how we can implement singular value decomposition, or SVD, in C++. In the SVD reduction function, we start by including the necessary headers from the Eigen library, which provides efficient linear algebra operations. The function takes in a matrix data and an integer target dim, which signifies the desired number of dimensions for our reduced output. We begin by creating an instance of BDCSVD, a class from the Eigen library which efficiently computes the SVD of the input matrix. With the Eigen, compute thin U, and Eigen, compute thin V options, we ensure that the resulting matrices U and V are calculated in a memory-efficient way. After computing the SVD, we extract the matrices U, sigma, sigma, and V, where U contains the left singular vectors, sigma holds the singular values in a diagonal matrix, and V contains the right singular vectors. Next, we select the top k components of U and their corresponding singular values from sigma. By utilizing left cols target dim for U and top left corner target dim for sigma, we effectively reduce the dimensionality of our data. Finally, we reconstruct the data in this reduced space by multiplying these selected components. The result, printed to the console, showcases the reduced data obtained via SVD, highlighting how we efficiently capture the most significant features while simplifying the dataset's structure. Let's take a moment to explore the differences and similarities between PCA and SVD. While they can be closely related, understanding when to use which is key. PCA focuses on the directions of maximum variance identified through eigenvalue decomposition of the covariance matrix, while SVD operates directly on the data matrix itself, regardless of shape. In practice, SVD tends to be more stable and versatile, especially for large datasets or non-square matrices. Further, if computational resources are a concern, SVD is often preferred due to its ability to handle sparse matrices more effectively when implemented properly. This means that in some contexts, SVD can not only achieve lower dimensionality but do so in a way that preserves computational efficiency. Now let's implement the independent component analysis, ICA, using C++. In our example, we include the necessary standard libraries and a placeholder for the ICA library, which contains the specific implementations needed to perform the analysis. The ICA example function is designed to take an input matrix data, along with an integer num components, indicating the number of independent components we wish to extract. Within this function, we declare an eigen, matrix XD variable named separated data, which will hold the resulting independent components after they are extracted. We then call the hypothetical performICA function, passing in the original data and our separated data variable. This function is crucial as it contains the underlying algorithms to separate the mixed signals into independent components based on statistical properties. Finally, we print out the separated source signals to the console, allowing us to view the results of our ICA implementation. This process of separating mixed signals is particularly useful in fields such as signal processing and neuroscience, where ICA shines in extracting meaningful patterns from complex datasets. By mastering this function, you will enhance your ability to analyze and interpret complex datasets effectively. As we continue exploring dimensionality reduction techniques, it is valuable to keep in mind that linear methods like PCA and SVD work well when the relationships within the data can be represented adequately using linear transformations. However, when the data structure is inherently complex and nonlinear, we may need to turn our attention to nonlinear techniques like TSNE or autoencoders, which excel at capturing such intricate patterns. However, for our current discussion on linear methods, sticking to PCA and SVD provides an excellent foundation. Remember, the aim of dimensionality reduction is to simplify data analysis, making interpretation and visualization clearer without losing significant amounts of information. In essence, the process of linear dimension reduction can dramatically enhance your data analysis capabilities by stripping away redundant features while preserving critical information. Whether you choose PCA to maximize variance or SVD for its robustness and stability, understanding these methods inside and out will empower you to tackle increasingly sophisticated datasets. In this journey of exploring linear methods for dimensional reduction, mastering these techniques will set you up for success in the complex field of data science. As we wrap up, remember to practice these implementations, experiment with different datasets, and appreciate how linear dimension reduction can unfold new insights from even the most challenging data. In the realm of machine learning, classification stands out as a pivotal task, guiding us in the journey of understanding and interpreting data. Essentially, classification is the process of dividing a set of observations into predefined categories based on their characteristics. This ability to segment data into meaningful classes empowers a plethora of applications, from predicting customer behaviors in business to aiding in medical diagnoses. Today, we'll delve into an overview of classification methods, exploring the various strategies that machine learning offers for tackling this task. So far, we have learned about the significance of dimensionality reduction techniques, focusing specifically on principal component analysis (PCA) and singular value decomposition (SVD). we uncovered how PCA identifies new axes of variance in data through eigenvalue decomposition, and SVD facilitates dimensionality reduction by factorizing matrices into 3 components. Additionally, we explored the differences between PCA and SVD, emphasizing that SVD's stability and efficiency make it preferable for large datasets. Moving forward, we will continue our exploration of linear methods and their applications in data analysis, specifically in the context of classification. Now let's see how we can implement logistic regression in C++. The class logistic regression initializes with a learning rate and a maximum number of iterations for the optimization process. Within the fit method, we begin by determining the number of training examples and the number of features, subsequently initializing our weights to 0. We then enter an iterative loop for optimization. For each iteration, we calculate the predictions for all training examples using the predict probability method, which computes the logistic function ensuring output values remain between 0 and 1. This function reflects the probability of an observation belonging to the positive class. After generating predictions, we compute the gradients for each feature to adjust the weights accordingly. The gradients are calculated by measuring the difference between predictions and actual labels, scaled by the features associated with those observations, allowing us to update the weights based on the learning rate and the number of examples. By iterating through this process, we refine our model's weights, enhancing its accuracy in predicting binary classifications. This straightforward yet powerful approach exemplifies how logistic regression works under the hood, ensuring our predictions evolve closer to the true outcomes with each pass. Next, we will write the following code to implement the k-nearest neighbors (KNN) algorithm. This implementation begins with the inclusion of necessary libraries, followed by the definition of a KNN class. The class constructor initializes the number of neighbors, k, that will be considered during classification. The fit method is used to store the training data and corresponding labels, which will be used for making predictions. Now let's see how the predict function operates. It calculates the Euclidean distance between a given query point and every point in the training dataset. This distance information is stored in a vector of pairs, where each pair consists of the distance and the associated label. After accumulating all distances, we sort this vector to identify the closest training points. Next, we count the votes among the k nearest neighbors using a map to tally the labels. The predicted class is determined by selecting the label with the highest vote count. Lastly, the method returns the predicted label, concluding the classification for the query point. This straightforward approach effectively captures the essence of KNN, emphasizing its reliance on distance metrics and majority voting for classification tasks. Now let's implement a basic support vector machine, SVM, in C++. This class begins by defining a constructor that accepts a penalty parameter, C, which influences the model's complexity and regularization. The fit method, which is crucial for training the model, takes in the feature matrix X and the labels Y, though the actual implementation of the training process is not detailed here. This would typically involve optimization techniques to find the optimal hyperplane that separates the classes effectively. Next, we have the predict method, which is designed to determine the class of a new observation based on its position relative to the hyperplane. Currently, this function is a placeholder and returns 0, indicating that the logic for classification based on the decision boundary still needs implementation. Lastly, the class contains attributes like the penalty parameter and a vector for storing the learned weights, highlighting the core elements that will influence the model's decision-making process. This structure lays the groundwork for expanding SVM's capabilities by incorporating features like kernel functions to tackle nonlinear classification problems in future implementations. In conclusion, we've covered an overview of classification methods extensively. We started from understanding the basics of classification tasks, moving through various algorithms like logistic regression, KNN, and SVM. Each method serves a unique purpose and is adaptable depending on the specific dataset and business objectives. Understanding the strengths and weaknesses of these classification strategies can empower data scientists and machine learning practitioners to make informed decisions that yield better predictive performance. In our subsequent discussions, we will delve deeper into advanced topics such as ensemble learning methods, where we'll explore how combining multiple classification approaches can lead to improved accuracy and generalization. Stay tuned as we embark on this journey towards mastering the art and science of machine learning. Now that we've discussed what the classification task is, let's look at various classification methods. These methods are essential tools in machine learning, allowing us to categorize data effectively. So far, we learned about the foundational concepts of classification in machine learning, emphasizing how observations are represented as vectors in n-dimensional space. We explored various classification methods, including logistic regression, k-nearest neighbors, KNN, and support vector machines, SVM, each offering unique strategies for mapping input data to predefined categories. Additionally, we discussed the practical applications of these methods across various sectors, such as business and healthcare. Moving forward, we will investigate advanced topics like ensemble learning to enhance classification performance. Now let's take a look at a C++ implementation of a logistic regression model. This class, named logistic regression, begins by defining the constructor, which initializes the learning rate and the maximum number of iterations for the fitting process. Next, the fit method takes in a dataset represented as a matrix of features x and a vector of labels y. Here, we determine the number of samples and features, initializing the weights vector to zeros. The core of the algorithm lies in an iterative process where, for each iteration, we first compute the predicted probabilities for all samples using the predict probability method. Once we have these predictions, we calculate the gradients for updating the weights using gradient descent. Essentially, we're ensuring that our predictions become increasingly accurate in relation to the actual classes. The learning rate controls the size of these updates, and with each iteration, the model refines its weights to achieve better predictions. Finally, the predict probability function calculates the probabilities based on a linear combination of weights and features, applying the logistic function to transform these into probabilities between 0 and 1. This encapsulates the inner workings of logistic regression effectively. Now let's see how we can implement the k-nearest neighbors algorithm in C++. The foundation of our KNN implementation is encapsulated within a class called KNN, which is initialized with a parameter k that determines how many nearest neighbors will be considered during classification. The fit method serves to store the training data and corresponding class labels. It takes in the input feature set x and the labels y, effectively setting up the model for predictions. Moving forward, the predict method is crucial as it computes the class label for a given query point. This method first calculates the Euclidean distance between the query point and each point in the training data. It achieves this using the Euclidean distance function, which applies the distance formula within a loop over the dimensions of the input vectors. Once the distances are calculated, they are sorted to identify the k closest points. A voting mechanism is employed next, where a map keeps track of how many times each class label appears among the nearest neighbors. Finally, the class label with the highest vote count is selected as the predicted label, demonstrating the essence of the k-nearest neighbors algorithm in a straightforward yet effective manner. Now let's see how we can implement a support vector machine SVM in C++. The SVM class begins with a constructor that takes a penalty parameter, denoted as C, which controls the trade-off between maximizing the margin and minimizing classification error. This parameter influences how flexible the decision boundary can be. Next, we look at the fit method, which is fundamental for training our SVM model. In this simplified version, we prepare to optimize the separating hyperplane based on provided training data, although the actual implementation of the optimization process is not shown here. It's important to note that this method will be crucial in deriving the weights that define our hyperplane. Then we implement the predict method, which determines on which side of the hyperplane a new instance falls. In our current placeholder setup, it simply returns a value of 0, indicating that we're yet to include the logic to return a definitive class label. This method will eventually utilize the calculated weights to help classify new instances effectively. Lastly, the class also houses a private member for weights, which will hold the learned parameters. The inclusion of the Armadillo library suggests that we can leverage its capabilities for efficient matrix operations, which are essential for SVM computations. Next, we will implement the decision tree class, which embodies a fundamental classification method in machine learning. This class will allow us to construct a decision tree that classifies data based on features. The fit method is responsible for building the decision tree using training data, represented by a 2D vector x for features and a vector y for labels. Although the implementation details are not fully fleshed out in this placeholder version, the core idea is to split the dataset based on feature importance, enabling the model to learn from the patterns in the data. Following the creation of the decision tree, the predict method takes a new sample, represented as a vector x, and traverses the constructed tree to classify it into one of the predefined categories. The method concludes with a placeholder return value, which ultimately should provide the predicted class label. This structure not only lays the groundwork for understanding how decisions are derived from data, but also highlights the interpretability of decision trees, making them a powerful tool for both classification tasks and gaining insights into data-driven decisions. To sum it all up, we have journeyed through a spectrum of classification methods, from logistic regression and KNN to SVM, decision trees, and random forests. We've seen how diverse strategies cater to unique challenges in classification tasks. Each method has its advantages and ideal applications, making the choice of classifier crucial based on the dataset characteristics and goals. As we move forward, we will delve into advanced topics, emphasizing ensemble learning and model optimization to enhance classification performance. With the foundational knowledge you've gained, you are becoming well-equipped to tackle real-world classification problems with confidence. Keep your seatbelts fastened. There's much more to explore in this exciting world of machine learning. Recommender systems are algorithms, programs, and services that analyze data to predict which items, such as goods or services, may interest a user. They play a crucial role in enhancing user experiences across platforms like online retailers, streaming services, and social media. Essentially, recommender systems sift through vast amounts of data, drawing insights that help individual users discover products tailored to their preferences. So far, we've covered various classification methods in machine learning, including logistic regression, k-nearest neighbors, KNN, and support vector machines, SVM. We've explored how these techniques function, their applications in real-world scenarios, and the significance of selecting appropriate classifiers based on dataset characteristics. Moving forward, we will delve into recommender systems, exploring how they function and the various approaches they utilize to provide personalized recommendations. To clarify further, a recommender system's essence lies in predicting a customer's preferences based on their past interactions. These interactions could include purchases, search history, or viewed items. By analyzing this data, these systems can recommend products users may be interested in, increasing the likelihood of conversions in online shopping or keeping them engaged in streaming services. For example, if you have recently bought fitness gear from an online store, a recommender system might suggest running shoes or workout gear that aligns with your purchases. The functionality of recommender systems can broadly be categorized into two main types: content-based filtering and collaborative filtering. Content-based filtering recommends items similar to those users have previously interacted with, while collaborative filtering suggests items based on the behavior of similar users. Each of these methods leverages the vast amounts of data generated through user interactions to make informed recommendations. Now let's implement a simple content-based recommendation system using C++. The first part of our code defines a function for calculating cosine similarity, which is a measure of how similar two items are based on their feature vectors. This function computes the dot product of the two vectors and divides it by the product of their magnitudes, allowing us to quantify the similarity score. Next, we create an unordered map to store item profiles where each item is associated with its corresponding feature vector. The addItem function helps us populate this map by taking an item's name and its features as input, effectively building a database of items and their attributes. Now let's see how we can utilize this data when a user interacts with the system. The recommendItem function takes in a user profile vector, representing the user's preferences, and iterates through the item profiles to find the one with the highest cosine similarity score. This function returns the name of the item that best matches the user's interests. Finally, in the main function, we demonstrate the system by adding movies with specific features and recommending one based on a user's preferences, showcasing the system's ability to suggest relevant items. Now let's see how we can implement user-based collaborative filtering using Pearson correlation to recommend users based on their ratings. We begin by defining a Pearson correlation function that takes two vectors of user ratings as input. This function calculates the mean ratings for both users, then iterates through their ratings to compute the numerator and denominators needed for Pearson correlation. The result gives us a measure of similarity between two users based on their rating behavior. Next, we maintain a user ratings unordered map to store the ratings of different users. The addRatings function enables us to populate this map by associating a user's name with their corresponding ratings vector. Following this, we implement the recommendForUser function, which searches for the user with the highest correlation to the current user's ratings. It does this by iterating through all users stored in user ratings, calculating the correlation for each, and updating the best match when a higher correlation is found. In the main function, we simulate this by adding two users and their ratings. Then we define a current user's ratings to generate a recommendation based on the closest user correlation. This approach demonstrates how collaborative filtering can leverage shared experiences to inform new user recommendations. Despite its potency, collaborative filtering has its drawbacks. The cold start problem is a prime challenge, arising when new items lack ratings or when new users begin using the system without any existing interaction data. Solutions often involve incorporating demographic data or implementing hybrid models that capitalize on content-based approaches alongside collaborative recommendations. For example, a typical strategy to mitigate the cold start problem includes employing content-based filtering, as we discussed earlier, to recommend items based on genre or category information while waiting for enough ratings data to make accurate collaborative filtering decisions. It's essential to wrap our heads around what makes recommendations relevant. Beyond analyzing the data generated through user feedback, recommender systems need to constantly factor in the freshness of content. Recently launched products or trending items must hold a position of significance in the recommendation lists, as this aids in driving user engagement. Take, for example, an e-commerce platform. If a new mobile phone is released, it should ideally appear prominently in recommendations, coupled with items that align with a user's previously expressed preferences. Incorporating a recency factor helps avoid situations where systems recommend outdated items, keeping the suggestions appealing and current. In this segment, we've explored the fundamental concepts surrounding recommender systems, diving deep into content-based filtering and collaborative filtering methods. Additionally, we looked into critical issues like cold start problems and the relevance of recommendations, stressing the importance of adapting to user needs. Next, we will enhance our understanding of how to implement these systems from a practical standpoint, leveraging existing libraries and frameworks effectively. In the upcoming sections, we will explore matrix factorization techniques, delve into the practical implementation of collaborative filtering using C++ libraries, and discuss how the frequent model assessment further fine-tunes the quality of recommendations. We aim to furnish you with the tools and knowledge necessary to create functional, efficient, and personalized recommender systems that cater to user needs across diverse platforms. Collaborative filtering is a powerful technique used in recommender systems to predict a user's preferences based on the preferences of similar users. This method hinges on the idea that if two users have similar taste in the past, they are likely to enjoy similar items in the future. In short, we'll delve into the mathematics and mechanisms of collaborative filtering and explore its implementation using C++. So far, we learned that recommender systems analyze user data to predict interests, enhancing experiences on platforms like streaming services and online retailers. We've discussed content-based filtering, which recommends items based on item attributes and user preferences, and collaborative filtering, which relies on user similarities for recommendations. We also touched upon challenges such as the cold start problem and the importance of keeping recommendations relevant and up-to-date. Moving forward, we will focus on implementing matrix factorization techniques and practical applications of collaborative filtering. Now let's implement the user-item interaction matrix we discussed. In the code, we first include the necessary libraries, such as IOStream for input-output operations and vector to utilize dynamic arrays. We define constants for the number of users and items to maintain clarity and flexibility within our program. Next, we create a function called printInteractionMatrix, which takes a 2D vector as input to represent the ratings and prints out the interaction matrix. This function utilizes nested loops to iterate through each rating and neatly formats the output, making it easy to visualize the ratings assigned by users to different items. In the main function, we establish our user-item interaction matrix using a two-dimensional vector. Each row corresponds to a user, and each column represents a movie they've rated. For instance, a rating of 5 by user 1 for the first movie demonstrates their high preference, while a 0 indicates that they haven't interacted with that item. Finally, we call the printInteractionMatrix function to display our matrix. This setup allows us to strengthen our understanding of how collaborative filtering utilizes user ratings to make item recommendations. Now let's implement a function to calculate cosine similarity, a crucial metric for measuring the similarity between users based on their ratings. In the cosine similarity function, we take two vectors representing users' ratings as input. The method begins by initializing variables to compute the dot product and the magnitudes of both rating vectors. As we iterate through the ratings, we accumulate the dot product and the squared magnitudes for each user. After iterating, we check if either magnitude is 0 to avoid division by 0, which would indicate that one of the users has not rated any items. If so, the function returns a similarity score of 0. Otherwise, we compute the cosine similarity by dividing the dot product by the product of the two magnitudes, providing a similarity score ranging from -1 to 1. Next, we will use this function in the main program to determine the similarity between two specific users. By initializing their ratings as vectors, we can call cosine similarity with these vectors and print the resulting score, helping us understand how closely their preferences align based on their ratings. Now let's see how we can implement the recommendation logic using collaborative filtering. The recommendItems function begins by initializing two vectors, similarities and user weights, to store the similarity scores between users and the weighted scores for items, respectively. We then calculate similarity scores for all users in relation to the target user, excluding the target user's own ratings. This is done by computing the cosine similarity between the target user's ratings and each other user's ratings. Next, we iterate through each user's ratings and check for items that the target user has not rated yet. For each unrated item, we multiply the user's similarity score with the rating they gave to that item, which enables us to weigh the importance of each similar user's ratings when generating recommendations. After all ratings are processed, we compile a list of indices for items that have a positive weight, suggesting that these items are likely to be of interest to the target user based on the preferences of similar users. Finally, in the main function, we define a small user-item interaction matrix and call our recommendItems function to get recommendations for user 1, outputting the indices of the recommended items that user 1 may enjoy. Understanding limitations is just as important as mastering theory and application. Collaborative filtering methods can suffer from issues like sparsity in the user-item interaction matrix. This sparsity arises when only a few users have rated certain items, resulting in limited data for generating meaningful recommendations. Additionally, there's the cold start problem, which occurs when new users or items lack enough interaction history for accurate recommendations. To address these concerns, hybrid recommendation systems combine collaborative filtering with other methods. For example, content-based filtering can complement collaborative filtering by leveraging item attributes to improve the recommendation accuracy for new items. By employing both methods, you create a richer dataset that enhances the prediction capabilities of your recommender system. An effective way to tackle sparsity and cold start problems is through matrix factorization techniques, which help approximate the user-item interaction matrix into lower-dimensional matrices. This approach reduces the dimensionality of the data, capturing latent features that can be used in predicting unknown user-item interactions. Matrix factorization tactics include singular value decomposition, SVD, and alternating least squares, ALS. Let's take a closer look at the math behind SVD. Imagine decomposing your user-item interaction matrix /r/ into three matrices, /u/, sigma / and /vt/, where /r equals u /sigma vt/. Here, /u/ represents user features /sigma contains singular values indicating the strength of correlations, and /v/ represents item features. By approximating /r/, we can capture key preferences and enhance our recommendations. Implementing SVD can be complex, but libraries like Igen in C++ provide functionalities that streamline this process. However, I want to keep this discussion focused on understanding the concept rather than diving deeply into matrix algebra at this point. As we progress, remember that the quality of recommendations is significantly influenced by the choice of similarity metrics, parameters used for matrix factorization, and nature of the dataset. Experimenting with different approaches and tuning their parameters can lead to better performing recommender systems. It's crucial to evaluate the effectiveness of your recommendation system thoroughly. Tools such as mean absolute error (MAE) or root mean square error (RMSE) can be employed to measure accuracy in predicting user ratings. In the upcoming segments, we will implement matrix factorization techniques and further explore practical applications of collaborative filtering based on our learned knowledge. With a firm grasp of collaborative filtering principles, you'll be well equipped to tackle more sophisticated recommendation systems. In conclusion, we've walked through the world of collaborative filtering, understanding its foundations, including the user-item interaction matrix, how to compute similarity scores between users, and the algorithms that can help recommend items based on preferred choices. Collaborating filtering represents a core concept in building intelligent recommender systems. As we move forward, your next steps will involve applying these principles in real-world scenarios, further enhancing the user experience through personalized recommendations. Ensemble learning leverages the power of multiple algorithms to improve predictive performance, creating a stronger and more reliable model. In essence, it combines a collection of weak learners to produce a robust predictive model that can surpass the capabilities of individual algorithms. So far, we've learned about collaborative filtering, which predicts user preferences by analyzing interactions between users and items. We discussed how similarity scores inform recommendations and explored challenges like the cold start problem. Now, let's turn our focus to ensemble learning, a technique that combines multiple models to enhance accuracy and reduce overfitting. The core concept of ensemble learning revolves around the training of a group of models, aggregating their results to enhance overall predictions. The The procedure is straightforward yet powerful. We first train several elementary algorithms, often referred to as base learners. Each of these models contributes to the final prediction via averaging or voting. There are two primary approaches to ensemble learning: bagging and boosting. Now let's dive into the implementation of the bagging technique using C++. We start by defining a decision tree class that simulates the training of a decision tree. The train method of this class takes a dataset as input and simply outputs a message indicating that it's training on a certain number of samples. This serves as a placeholder for a more complex training algorithm typically found in real decision tree implementations. Next, we introduce the bagging class, which is responsible for managing multiple decision trees. In the constructor, we initialize a vector of decision tree objects based on the specified number of trees. The main job of the bagging class is to generate bootstrap samples of the dataset. The generateSamples method uses a random number generator to create multiple samples from the provided dataset, ensuring that each tree is trained on a different subset. Finally, the train method iterates through each tree and calls its train method, parsing in its respective sample. This training process reduces variance by averaging the predictions from different trees when they make their final predictions. In the main function, we create a sample dataset, instantiate the bagging class, generate the samples, and initiate the training process. This implementation effectively illustrates how bagging can be realized programmatically, showcasing its potential for improving model robustness. Now let's walk through the implementation of boosting in C++. The code begins with the definition of a weak learner class, which simulates a weak predictive model. This class includes a train method that takes in a dataset and corresponding labels, simulating the training process by printing a message to indicate that a weak learner is being trained. Next, we have the boosting class, which is responsible for managing a sequence of weak learners. It contains two private members: a vector of weak learner objects to store the trained learners and a vector of weights to keep track of the importance of each instance in the dataset. The train method of the boosting class is where the ensemble learning magic happens. It loops through a predefined number of iterations, here exemplified with 10 weak learners, and trains each one sequentially. After training each learner, the weights are updated based on their performance. Although this implementation of weight adjustment is simplified, it hints at the more complex strategies often employed in boosting algorithms like AdaBoost. Finally, the main function demonstrates how to use the boosting class by creating a dataset and corresponding labels, followed by calling the train method to build the boosting ensemble. This setup prepares the foundation for effectively improving predictive performance through sequential model training. Now let's implement the following averaging function that will serve as the aggregation method for our ensemble learning predictions. The average function is designed to compute the mean of a list of predictions, which is vital for combining the outputs from multiple models effectively. Inside the function, we initialize a variable sum to accumulate the total of the predictions. A for each loop iterates through each prediction in the provided vector, adding each value to the sum. After summing all the predictions, the function returns the result by dividing the total sum by the size of the predictions vector, giving us the average value. In the main function, we create a vector of sample predictions to illustrate how the average function works. By calling the function with this vector, we calculate the average prediction and store it in the variable avg prediction. Finally, the program outputs the calculated average to the console, demonstrating the function's capability to aggregate results from different model predictions into a single, coherent value, which is essential for improving the overall accuracy of our ensemble learning framework. Ensemble learning also shines in its applicability to various fields, from finance to healthcare to image recognition. Its versatility allows practitioners to apply these strategies to a wide array of datasets, improving performance reliably. However, it's essential to understand the trade-offs. Ensembles are computationally more expensive than single models, and their complexity can sometimes lead to issues in interpretability. As we wrap up this overview of ensemble learning, we have covered the fundamental concepts, methods, and implementations. We've learned how bagging and boosting can train multiple models to combine their predictions effectively, illustrated with C++ code examples. In the next installment, we will dive deeper into specific ensemble techniques like random forests and gradient boosting machines, GBMs, exploring their architectures, hyperparameters, and real-world applications to gain a more profound understanding of why they are favored in practice. Thank you for joining this session, and I look forward to wandering deeper into the ensemble jungle with you next time. Keep coding and stay curious. To show the implementation of more ensemble learning techniques, we can develop the stacking approach manually. Today, we're going to dive deep into the world of stacking ensembles, an advanced ensemble method that allows us to build a model that combines the predictive strengths of various models into one powerful entity. This technique often yields better predictive performance by leveraging the unique strengths of each individual model within the ensemble. So far, we have learned about ensemble learning, which enhances predictive performance by combining multiple algorithms, specifically through techniques like bagging and boosting. Bagging reduces variance by training models independently on different data subsets, while boosting sequentially builds models that focus on correcting previous errors. We also explored simple C++ implementations of both techniques alongside aggregation methods for combining predictions. In this lesson, we're going to cover the implementation of stacking ensembles, exploring how to structure our models in a way that maximizes their collaborative potential. Now let's implement the first part of our stacking ensemble by defining three essential classes: decision tree, logistic regression, and meta-learner. The decision tree class includes a predict method, which returns a simulated prediction by performing a simple weighted sum of the input features. Similarly, the logistic regression class also contains a predict method, but it uses a basic logistic function to simulate more complex behavior. Both classes are designed to simply demonstrate model predictions, and in actual practice, these would entail more sophisticated algorithms. Next, we introduce the meta-learner class, which is responsible for combining the predictions from our two base models. It uses simple weights for each model's prediction to create a final output, showcasing how predictions can be aggregated. Following the class definitions, it's time to bring these components together in our main function. Here we start by setting up a small dataset of feature vectors. After instantiating our base models and the meta-learner, we collect predictions from the decision tree and logistic regression models. The final predictions vector then contains aggregated results, illustrating how a stacking ensemble can provide enhanced predictions by leveraging the strengths of each base model. Now let's implement the k-fold cross-validation approach to enhance our stacking ensemble. We start by defining a function, perform k-fold cross-validation, which takes our dataset and the number of folds as parameters. Within the function, we determine the size of each fold and instantiate our base models: decision tree, logistic regression, and the meta-learner. Next, we enter a loop that iterates over each fold. During each iteration, we separate our dataset into training and validation sets based on the current fold index. This separation allows us to ensure that the model is trained on certain subsets while being validated on others, promoting a robust evaluation of our predictions. As we gather predictions from both base models using the training data, we store these predictions for the respective validation samples. These predictions are then passed to the meta-learner, which combines their outputs to yield a final prediction for each fold. Finally, we print out the meta-predictions for each fold, showcasing how the model performs across different portions of the dataset. This comprehensive process reinforces the effectiveness of stacking by validating the ensemble's predictions and helping to minimize the risk of overfitting. Now let's take a look at how we can implement a grid search for hyperparameter tuning in our models. We'll begin by defining the hyperparameter tuning class, which contains a method called grid search. This method takes parameters such as max depth and min sample split, which are essential for configuring decision trees. Inside this method, we simply print out the combinations of hyperparameters being tested. In a practical application, this section would include the logic for training the decision tree using these parameters and evaluating the results on a validation set to identify the best configuration. Next, we implement the perform grid search function, where we create an instance of hyperparameter tuning. We define ranges for the depth and split parameters using vectors, allowing us to systematically explore combinations. The function uses nested loops to iterate through each depth and split value, calling the grid search method for every combination. This structured approach enables thorough exploration of the parameter space. Lastly, when we invoke perform grid search in the main function, we effectively execute the grid search process, showcasing how hyperparameter tuning can enhance our stacking ensemble models for better predictive performance. Finally, let's wrap up by reflecting on the power of stacking ensembles and how they allow us to draw the best out of multiple base algorithms. When implemented correctly, stacking can outperform individual models, harnessing their unique capabilities to improve overall predictions. It's important to note that while stacking increases predictive performance, it also adds complexity and computation time, which are necessary trade-offs in the quest for better accuracy. More importantly, the choice of base models, the meta-learner, and hyperparameter settings all play crucial roles. Through this lesson, we've explored stacking ensembles from the ground up, from understanding their architecture to implementation using C++. We've also touched on k-fold cross-validation, predictions aggregation, and hyperparameter tuning strategies. Now that you're equipped with the knowledge of implementing stacking ensembles, you're ready to tackle real-world problems with more sophisticated models that can collaborate effectively for superior predictions. So keep pushing forward, experiment with different algorithms, and who knows, you might invent the next cutting-edge machine learning model. Happy coding, and see you in the next lesson. Artificial neural networks have become one of the most exciting and transformative areas in machine learning today. With their inspiration drawn from the human brain, these networks are designed to recognize patterns, make predictions, and even learn from data in ways that were once considered the realm of science fiction. In this session, we will explore the fundamentals of neural networks, their historical development, operational principles, and why they have gained such prominence in the field of artificial intelligence. So far, we learned about ensemble learning techniques, including bagging and boosting, which enhance predictive performance by combining multiple models. We delved into the stacking ensemble method, where multiple base models generate predictions that are then combined by a meta-learner for improved accuracy. Additionally, we covered the implementation of stacking ensembles using C++ and the importance of k-fold cross-validation to ensure robust model training. Finally, we discussed hyperparameter optimization to further enhance the performance of our ensemble models. Now we will talk about what artificial neural networks are, how they evolved, and the fundamental concepts behind their operation. To start, let's define what an artificial neural network is. At its core, a neural network is a computational model inspired by the way biological neural networks in the human brain process information. These networks consist of interconnected groups of artificial neurons that work together to solve complex problems. Each neuron receives inputs, applies a mathematical transformation, and produces an output that can serve as an input for other neurons. The magic happens as these networks learn from data. They adjust the connections, called weights, between neurons based on the learning process, allowing the model to improve its predictions over time. Now let's take a look at how we can implement a basic structure of a neural network using C++. The neural network class serves as the foundation of our model, encapsulating the essential features required for the neural network's operation. The private member variables input layer size, hidden layer size, and output layer size represent the number of neurons in each respective layer, determining the architecture of our network. In the constructor, we initialize these variables with the provided parameters, allowing for flexibility in configuring the network size based on the specific problem we're addressing. Although there's a placeholder comment for initializing weights, this is a critical aspect of the neural network's learnability, as the weights dictate how inputs are transformed and propagated through the layers. The forward propagate function is pivotal, as it will eventually hold the logic for passing inputs through the network. Though currently unimplemented, this function is where the computations occur, translating the input data into predictions. This basic framework sets the stage for more complex functionalities, such as training and prediction, which can be added as we expand our neural network's capabilities. Now let's see how we can implement a simple version of the backpropagation algorithm in our neural network. The first step in this function is to initialize a vector called errors, which will store the difference between the expected outputs and the predicted outputs for each neuron in the output layer. We achieve this by iterating over the size of the output layer and calculating the error for each output neuron. Specifically, we subtract the predicted value from the expected value, capturing how off our predictions are. This step is crucial for understanding how well the neural network is performing and highlights the areas where it needs improvement. Once we have the errors calculated, the next logical step, though not explicitly shown in the code snippet, would be to adjust the weights of the network based on these error values. This adjustment is fundamental to training the model, as it influences how the network will process future inputs and refine its predictions. By continuously updating the weights in response to these errors during training, the neural network learns over time to make more accurate predictions, effectively minimizing the error. This process is what enables the network to learn from the data it processes, forming the backbone of the training phase in neural networks. The evolution of neural networks has an interesting history. Initially, the concept of neural networks dates back to the 1940s with the work of Warren McCulloch and Walter Pitts, who created simple models of neurons. The 1980s saw the introduction of multi-layer perceptrons, which utilized backpropagation to achieve more complex learning tasks. However, enthusiasm waned during the late 1990s, often referred to as the AI winter, due to limited computational power and insufficient data. The resurgence of neural networks in the early 21st century was catalyzed by advances in hardware, particularly graphics processing units, GPUs, and vast amounts of data available for training these models. Now let's see how we can implement the RayLU activation function in our neural network design. The RayLU, or rectified linear unit, is a crucial activation function that helps introduce nonlinearity into the model, ensuring we can better capture complex patterns in data. In this implementation, we define a function that takes a double as input. The function checks if the input value is greater than 0. If it is, the function returns the input as is. Otherwise, it returns 0. This characteristic of the RayLU function allows the network to retain positive values while effectively disregarding negative ones, facilitating faster convergence during the training process. This behavior mitigates issues like the vanishing gradient problem that can emerge with other activation functions, such as sigmoid and tan, especially in deeper networks. Understanding and correctly implementing this function is essential for optimizing the training of neural networks, as it directly impacts how effectively the model adjusts its weights based on errors during learning. As we continue to develop our neural network, the RayLU function will be pivotal in activating neurons, driving the learning process forward. Now let's implement the training process for our neural network. The train function is designed to manage the learning loop, where the network iteratively refines its parameters based on the input data it receives. Within this function, we loop through a predefined number of epochs, which represent complete passes over the training dataset. For each epoch, we systematically process every training example in the dataset. As we encounter each input sample, we begin by invoking the forward propagate method. This method passes the input through the network, calculating the predicted output at each layer based on the configured architecture and weights. After obtaining this output, we proceed to call the backpropagate function. This function plays a crucial role in training by comparing the actual output, the labels, to our model's predictions, determining the prediction errors. This information is essential, as it enables the network to adjust its weights accordingly, effectively minimizing the prediction error. By repeating this process over several epochs, we allow the neural network to incrementally learn from the training data, improving its ability to classify inputs correctly as training progresses. Now let's take a look at how we can implement a basic convolutional neural network, CNN layer, by defining a convolutional layer class. This class is structured to include private member variables for storing the number of filters and the size of each filter. which are crucial components in the convolution operation. The constructor of the class initializes these variables, allowing you to specify how many filters are needed and what their dimensions will be. Next, we will implement the forward pass method, which processes the input through the convolutional layer. This method is responsible for applying the filters to the input data, performing the convolution operation, and subsequently applying an activation function to introduce nonlinearity. This step is essential as it helps the network learn complex patterns in the data, particularly in tasks like image processing. By encapsulating these functionalities within a well-defined class, we not only promote code reusability, but also enhance clarity and organization, making it easier to build more advanced architectures leveraging this foundational layer. This approach paves the way for effectively handling the intricacies involved in CNNs and ensures we have a solid ground for further enhancements. As we explore the implementations and the nuances of neural networks, it's critical to keep in mind the computational demands they entail. Training deep networks usually requires substantial resources in terms of memory and processing power, particularly with larger datasets. Modern frameworks like TensorFlow and PyTorch facilitate this by providing optimized functions and GPU support, but understanding the underlying principles enriches your appreciation of these powerful tools. As neural networks continue to evolve with new techniques like transfer learning and generative adversarial networks (GANs), their applications reach new heights from autonomous vehicles to medical diagnostics. Companies harness this technology not only to improve their products, but to innovate entirely new functionalities that reshape industries. In summary, we have covered the definition and architecture of artificial neural networks, their learning processes through backpropagation, the evolution of these networks, essential activation functions, and different advanced architectures. Understanding these fundamentals equips you to dive deeper into the intricacies of neural networks and their real-world applications. As you continue your journey into machine learning, keep the principles we've discussed in mind. They are the foundation upon which many modern AI systems are built. It's an exciting time to be involved in this field, as the potential of neural networks is only beginning to be realized. So, buckle up and prepare for an incredible journey into the world of artificial intelligence. In this lesson, we will implement a convolutional neural network, or CNN, for image classification. We will utilize the widely renowned dataset of handwritten digits known as the Modified National Institute of Standards and Technology (MNIST) dataset. You can find it at http://yanlecon.com/xdb/mnis/. So far, we covered artificial neural networks, their architecture, and the learning process through backpropagation. Now we will talk about how to implement CNNs, their structure, and practical applications using C++. Now let's see how we can implement the essential building blocks of our CNN by defining the neuron and layer classes. The neuron class represents a single neuron, encapsulating its activation level with the value attribute and its weights through a vector. When creating a new neuron, we randomly initialize its weights to prepare it for the training process. Next, we proceed to implement the layer class, which contains multiple neurons. This class houses the feed-forward method, which computes the neuron activations based on incoming inputs. Through a weighted sum of inputs, we leverage the sigmoid function to introduce nonlinearity, allowing the network to learn complex patterns. As we develop our CNN architecture further, it's crucial to understand how layers interact. Thus, we will integrate the convolutional and pooling functionalities next, allowing our network to extract significant features from input images effectively. These operations will utilize the convolutional layer class to manage filter application across images and the pooling layer class to condense the resulting feature maps, ensuring our architecture becomes both efficient and powerful for image classification tasks, specifically with the MNIST dataset. Now let's implement the pooling layer, which is crucial for further condensing the feature maps generated by the convolutional layer. The pooling layer class, initialized with a pool size, will extract significant features from the input by applying a pooling operation. The apply method takes the input feature map and computes the output by iterating through small regions as defined by the pool size. It uses max pooling, which means for each region it will identify the maximum value, effectively reducing the spatial dimensions while retaining the most important information. This operation not only helps in managing the complexity of the data, but also ensures that the network remains robust against small translations in the input images. The output of this pooling operation is then set up to flow into subsequent layers of the network for further processing, leading to enhanced feature extraction and classification performance. By iterating through the input, we achieve a substantial reduction in dimensionality, making the network more efficient while preserving essential features of the images. Now let's implement the following CNN class, which organizes our model's architecture. This class includes private members for a convolutional layer, a pooling layer, and a fully connected output layer, allowing us to build an end-to-end classification system. In the constructor, we initialize these layers. The convolutional layer features a 3x3 filter, which helps capture fine details in images. The pooling layer uses a 2x2 pooling operation to downsample the feature maps while retaining important spatial information, and the fully connected layer consists of 10 neurons, which corresponds to the digit classes we aim to classify. Next, we will write the forward pass method to manage data flow through our CNN. This method takes a vector of input images and first applies the convolutional layer to extract features, resulting in feature maps. These maps are subsequently processed by the pooling layer, which condenses the data further before flattening it into a one-dimensional vector. Finally, this flattened data is fed into the fully connected layer to produce outputs for classification, efficiently linking feature extraction with decision-making in the CNN framework. Now that we have defined the basic architecture of our CNN and discussed its layers, we need to implement the dataset loading and training processes. First, let's write the function that will load the MNIST dataset into our program. This function is essential as it extracts image and label data from the binary files, converting it into a format usable by our CNN. It involves opening the dataset files, reading through each entry, and populating our vectors with pixel values for the images and their corresponding labels, ensuring that they are prepared for training. Next, we will implement the training loop for our CNN. This loop is structured to run for multiple epochs, allowing the network to learn incrementally from the data. We will iterate over each image in our training dataset, executing a forward pass through the CNN. Each time the model processes an image, we will implement backpropagation logic to adjust the weights based on the calculated prediction and its corresponding label. This training process is crucial for minimizing classification errors, and we will log the completion of each epoch to monitor progress throughout the training phase. Now let's take a look at the function testCNN, which is crucial for evaluating the performance of our trained convolutional neural network, CNN. This function assesses how well the model can classify images it has not seen during training. It begins by initializing a counter for correct predictions, which will help quantify the model's accuracy. As we iterate through the test dataset, each image is fed into the CNN through a forward pass, allowing the model to generate predictions. At this stage, it is essential to implement the logic that determines the predicted class for each image. This entails comparing the CNN's output with the actual labels provided in the test set to see if they match. Every time a prediction corresponds with the true label, the counter for correct predictions is incremented. At the end of the iterations, the function calculates the overall accuracy by dividing the number of correct predictions by the total number of test images, giving us a measure of the CNN's performance expressed as a percentage. This feedback is vital for understanding how effectively our model can classify handwritten digits, paving the way for further refinements and improvements. As we reach the conclusion of our deep dive into convolutional networks, it's vital to elicit what we've learned. We explored the implementation steps of a CNN for the purpose of image classification, specifically addressing handwritten digits through the MNIST dataset. We defined the foundational classes necessary to construct our neural network, integrated convolution and pooling operations to extract features from images, and established a training loop that allows our model to learn from the data. Image classification with CNNs isn't just an academic exercise. These methods have tangible impacts in the real world, enabling advancements in computer vision, autonomous driving, and medical imaging. The journey of building a working CNN is both enlightening and rewarding, providing insights that pave the way toward more complex and capable deep learning architectures. Having laid the groundwork for image classification using CNNs, I encourage you to continue experimenting with modifications to our model. Try different filter sizes, batch normalization techniques, or even experiment with dropout layers to see how each affects performance. Learning is a continuous journey, and the more you practice, the better you'll become. Thank you for joining me on this tutorial about the implementation of convolutional networks. Keep coding, keep exploring, and I look forward to seeing you in the next lesson. The transformer architecture is a type of neural network that has revolutionized the field of natural language processing, NLP. It was first introduced in the renowned paper, Attention is All You Need, authored by a team of researchers from Google. This architecture has gained significant traction because of its powerful capability to process sequential data while efficiently capturing long-range dependencies. The transformer has established itself as a cornerstone for advanced NLP tasks such as translation, summarization, and sentiment analysis. So far, we learned about implementing a convolutional neural network, CNN, for image classification using the MNIST dataset. We discussed the foundational components of a CNN, including the architecture with convolutional and pooling layers, and how to define classes for neurons, layers, and the CNN structure in C++. We also covered the training process, including loading the dataset, executing forward passes, and adjusting weights through backpropagation to improve classification accuracy. Finally, we outlined the importance of validating the model's performance with a separate test dataset. Now we will talk about the essentials of the transformer architecture and how it operates fundamentally. The transformer architecture primarily consists of two components, the encoder and the decoder. The encoder processes the input sequence and transforms it into a set of continuous representations. The decoder, on the other hand, utilizes these representations to produce the desired output sequence. This division is particularly advantageous for tasks such as machine translation, where the input and output sequences have different lengths and structures. Next, we will implement the self-attention mechanism, which is crucial for enabling the model to weigh the importance of different words in the input sequence when generating its output. In this implementation, we start by calculating the attention scores, which are determined by taking the dot product between the queries and the transposed keys. This operation effectively measures how similar the queries are to the keys. To ensure stability in our calculations, the scores are scaled down by the square root of the dimension of the queries, allowing for a more balanced variance. Once we have the attention scores, we apply the softmax function to transform these scores into probabilities, highlighting which parts of the input the model should focus on. This results in the generation of attention weights that represent the degree of attention each word in the sequence should receive. Finally, we compute the attention output by performing a matrix multiplication of these attention weights with the values, allowing the model to generate a contextually aware output based on the input sequence. Now, let's take a look at how we can implement the feed-forward neural network that follows the self-attention operation. This component will independently process the output from the self-attention layer for each position in the sequence. The feed-forward network consists of two linear transformations with a ReLU activation function between them. This structure enables the model to further refine the representations learned from the self-attention step, effectively transforming them into a more meaningful and usable form for subsequent processing within the encoder stack. Now let's take a look at the implementation of the cross-attention mechanism. This function is crucial for the decoder. as it allows the model to focus on the relevant parts of the encoder's output while generating each token in the output sequence. This is achieved by calculating attention scores through the dot product of the decoder's queries with the keys from the encoder, facilitating a measure of how much attention each aspect of the input should receive. These scores are normalized using the softmax function, converting them into attention weights that sum to 1 and effectively highlight which parts of the input are most important. Next, we will write the positional encoding function, which addresses a key challenge in the transformer architecture. Since the model processes the data in parallel and has no inherent understanding of the token positions, we need to encode this information. In this function, we create position indices and apply a combination of sine and cosine functions to generate unique positional embeddings for each token. This allows the model to retain the sequence order, helping it understand the context of tokens in the input. Together, these functions are vital for ensuring the transformer can generate coherent and contextually relevant sequences. In addition to these core mechanisms, the transformer architecture also incorporates residual connections and normalization layers. The residual connections add the input of each sublayer to its output, which helps in alleviating the vanishing gradient problem during training. The normalization layers stabilize the training process and often boost convergence speeds. Implementing such mechanisms in your architecture provides robustness and speeds up the learning process, optimizing performance for various tasks. Finally, the adaptability of the transformer architecture to specific tasks is worth noting. Models such as BERT bidirectional encoder representations from transformers leverage only the encoder stack, while GPT generative pre-trained transformer utilizes only the decoder. This versatility allows researchers and engineers to employ the architecture for a wide range of applications, from sentiment analysis to machine translation, enabling quick adaptation to specific needs while retaining performance. In conclusion, the transformer architecture is not merely an advancement over previous models, but a groundbreaking framework reshaping how tasks are approached in NLP and beyond. Its layers facilitate nuanced understanding and dependencies that traditional architectures struggle to capture, demonstrating its superiority in handling complex sequential data. With this comprehensive overview of the transformer architecture, we are ready to deepen our understanding of how these concepts translate into robust applications, which we will cover in the next sections. Today, we dive into an exhilarating topic: the application of transfer learning using BERT, which stands for bidirectional encoder representations from transformers. This revolutionary approach has changed how we handle natural language processing tasks, from sentiment analysis to question answering. So far, we have learned about the transformer architecture, its encoder and decoder components, and various mechanisms that enhance learning performance. Now, we will cover the key steps involved in applying transfer learning with BERT in practical scenarios. To begin, let's outline what applying the transfer learning algorithm involves. We start by selecting a pre-trained model. Choosing the right model is crucial as it should be relevant to the target task. In the case of BERT, you would typically opt for one of the pre-trained models available via platforms like Hugging Face's Model Hub. This selection aids in leveraging the powerful knowledge already learned by the model on vast datasets, averting the need to start from scratch. Now, let's implement the function to load our pre-trained BERT model. This is essential because we need to utilize the rich feature representations that BERT offers for our specific NLP tasks. We start with the load BERT model function, which takes a string parameter representing the model's file path. By using the torch JIT load method, we can load the model into torch script, enabling us to run the pre-trained BERT model in our C++ environment seamlessly. Next, we will write the sentiment model class, which includes crucial components for our sentiment analysis application. Within its constructor, we load the BERT model and register layers required for our classification task. We include a dropout layer to mitigate overfitting, followed by a fully connected linear layer that maps the 768-dimensional output from BERT to our target classes, typically 2 for sentiment analysis. In the forward method, we apply the BERT model to our input data, extracting embeddings and passing them through dropout and then the linear layer. This structure allows us to benefit from BERT's robust feature extraction while tailoring the output to our specific classification needs. As we build our model this way, we ensure it is both efficient and effective for our sentiment analysis task. Now let's implement a class for our sentiment analysis model that incorporates the pre-trained BERT and adds a classification head. The sentiment model class inherits from Torch, NN, module, enabling it to leverage PyTorch's powerful capabilities. In the constructor, we initialize the model by loading the BERT model using a specified path, which allows us to use the features learned during its extensive training. To mitigate overfitting, we include a dropout layer with a rate of 0.1, registered with the module, and a fully connected linear layer that translates the output from BERT into class predictions, specifically targeting two classes relevant for sentiment analysis. Next, we define the forward method, which takes inputids and attention mask as inputs. Here we invoke the BERT model to obtain feature embeddings through a forward pass, applying dropout to these embeddings to enhance generalization. The output is then processed by the linear layer to produce class scores, which we convert to probabilities using the softmax function. This setup illustrates how we can effectively structure our model to utilize pre-trained knowledge while also customizing it for our specific task. Now let's see how we can implement the freezing of BERT parameters to retain the model's learned knowledge. We define a function that iterates through all the parameters of the BERT model and sets their gradients to false. This ensures that during backpropagation, these frozen parameters won't be updated, allowing only the new classification head we've added to learn from the training data. This is critical for transfer learning, as we want to leverage the extensive knowledge BERT has acquired without altering its foundational weights. Next, we will prepare our data loader to batch our dataset efficiently for training. By creating a data loader specific to the IMDb dataset, we can seamlessly manage how our data is fed into the model in batches, providing the model with a steady flow of input necessary for effective training. Now let's take a look at the training loop we will implement. This structure will guide our model through multiple epochs, updating the weights only for the new layers while keeping the BERT parameters unaltered. Within each epoch, we clear the gradients, perform a forward pass to get the model's predictions, compute the loss against the true labels with cross-entropy, and finally, backpropagate to update the model's weights using the optimizer. This iterative process continues until we achieve convergence, effectively training our sentiment analysis model on the new dataset. Now let's implement the evaluation phase of our model to assess its performance after training. First, we switch the model to evaluation mode using the model_eval command. This is crucial because it adjusts the behavior of certain layers like dropout and batch normalization to their evaluation settings, ensuring that the model makes predictions correctly without the random noise introduced during training. Next, we iterate through the test dataset using a for loop, which allows us to access each batch of data sequentially. Within this loop, we obtain the model's predictions by passing the input features through the model. It's important to compare these predictions against the true labels to compute evaluation metrics such as accuracy, precision, or recall. While the code does not explicitly show the calculation of metrics, this is the next logical step. By collecting these metrics, we can gauge how well our model is performing, identify potential areas for improvement, and make informed decisions about any necessary adjustments. Thus, this evaluation process is key to understanding the effectiveness of the transfer learning approach we've applied with BERT in our natural language processing task. In closing, the transfer learning approach through BERT opens up exciting possibilities for rapidly developing NLP applications that can understand and respond effectively to human language. So whether you're feeding sentences into your model for sentiment analysis or building a more sophisticated question-answering system, understanding and applying these concepts will place you at the forefront of NLP technology. The future is bright for those skilled in these methodologies, so keep exploring. In today's session, we will dive into the fascinating world of model serialization APIs in various C++ libraries such as dlib, Flashlight, MLpack, and PyTorch. Understanding how to save and load machine learning models is essential for deploying applications efficiently. So far, we covered the transformative impact of transfer learning using BERT for NLP tasks, focusing on key steps including model integration and training processes. Now we will cover model serialization APIs, a crucial topic for preserving the work we've done in our machine learning applications. Now let's see how we can implement model serialization in dlib, which allows us to save our trained models efficiently. In this example, we start by including the necessary dlib headers, including those for matrix operations, support vector machines, and serialization functions. Our main function begins with defining our types. We create a sample type, which is a 2x1 matrix of doubles, and a kernel type that uses a radial basis kernel. Next, we declare a decision function for our kernel. It's important to note that we assume this decision function has been trained with data before we proceed to serialization. The key part of this process is when we open an output file stream in binary mode to a file named model.dat. Here we utilize the serialize function from dlib, which takes care of writing the entire structure of our trained decision function to the specified file, including its parameters and configurations. Once the serialization is complete and the file is closed, our model is saved and ready for future use, enabling us to avoid retraining when we need to make predictions later. Now let's see how we can load a previously serialized model using dlib. First, we include the necessary dlib headers, which give us access to functionalities for matrices, support vector machines, and serialization. In the main function, we begin by defining a decision function with a radial basis kernel. This will hold our loaded model. Next, we open the binary file model.dat that we created earlier during the serialization process. Using an input file stream, we read the model's data into our decision function variable df. The deserialize function from dlib simplifies this process, automatically reconstructing the model's attributes for us. After successfully loading the model, we close the input stream to free up the resources. Now that we have our model ready, we can utilize it for predictions. Here we create a sample input using a matrix structure. We assign values to the sample features and then call the df function with the sample as input, which gives us the prediction result. This functionality allows us to make immediate predictions without needing to retrain the model, streamlining our workflow in machine learning applications. Now let's take a look at how to save a model using the Flashlight library. In this code, we first include the necessary header files required for Flashlight functionalities, such as handling neural networks and serialization. We then use the sequential class to create an instance of our model, which will allow us to layer multiple components together effectively. Next, we leverage the save function to write our model to a binary file named Flashlight ModelBin. This function is particularly powerful as it ensures that every detail of the model, including its architecture and parameters, is accurately preserved for later use. With the model saved, we can easily retrieve it in the future without the need for retraining, thereby streamlining our workflow and enhancing efficiency in deploying our machine learning applications. This method of serialization is essential for maintaining continuity in development, allowing us to focus on further improvements rather than starting from scratch each time we need to use our model. Now let's take a look at how to load a model in Flashlight, which is a straightforward process. In this example, we start by including the necessary Flashlight headers that facilitate model operations, such as loading, training, and defining neural network structures. The primary function, load, is utilized here to retrieve the model from the specified binary file, Flashlight ModelBin. By using the template parameter, sequential, we inform the function about the type of model we are expecting to load. Once the model is loaded into memory, we can use it for predictions immediately. To demonstrate this, we create a sample input tensor which is initialized to random values. This input simulates a typical data point that the model would consume for inference. We then invoke the forward method on the loaded model, passing our input tensor as an argument. This method computes the output by processing the input through the trained layers of the model, allowing us to make predictions without any additional setup. This seamless experience illustrates the power of model serialization in Flashlight, enabling easy transitions from training to inference. Now let's see how we can implement model serialization in MLPack, a powerful C++ machine learning library known for its efficiency and flexibility. The given code begins by including the necessary headers from the MLPack library, which provides the foundational components for machine learning tasks and decision tree algorithms. Within the main function, we initialize a decision tree classifier represented by the object dt. Although the code snippet omits the training step, you would typically train the model using a dataset before saving it. Once the model is trained, we utilize the MLPack serial save function to serialize the decision tree model into XML format. This function requires two arguments: the name of the file to save the model to, in this case, MLPackModel XML, and a string defining the model's identifier, decision tree. This approach allows for clear organization, especially when managing multiple models. After executing this code, you would have a file containing the complete state of your decision tree model, ready for later retrieval and use in making predictions. Now let's see how we can implement model loading using MLPack, a C++ library known for its efficiency in machine learning tasks. In this example, we start by including necessary MLPack headers, along with the decision tree method, which we will utilize for our predictions. Next, we define the main function and create an instance of the decision tree class. Now let's implement the model loading process. We will use the load function from the MLPack serialization module to retrieve our previously saved decision tree model from the XML file called MLPackModel XML. This step is crucial as it reconstructs our model in memory, allowing us to leverage it for making predictions without retraining. Once we've loaded the model, we define an input vector containing the features for which we want to make a prediction. Finally, we utilize the classify function provided by the decision tree instance to classify the input vector and obtain the prediction result. This entire process demonstrates the seamless integration of saving and loading models, facilitating easy model management and deployment in machine learning applications. Now let's see how we can implement model serialization using the popular PyTorch library in C++ with the libtorch interface. The code begins with including necessary headers for PyTorch, which allow us to work with tensors and scripting functionalities. Inside the main function, we first create a random tensor as a placeholder, simulating a tensor that might be used in a model. This step demonstrates how to initialize a tensor, which represents the data in our model. Next, we assume that a model has already been defined, though for illustrative purposes this specific model definition is not shown in the code. The core feature of this snippet is the torch save function, which is called to serialize the model and save it to a file named PyTorchModel PT. This function not only captures the model's architecture, but also preserves its parameters and configurations, ensuring that we can easily retrieve and reuse the model at a later time. Thus, with just a simple function call, we can store the complete state of our trained PyTorch model efficiently. Now let's see how we can load a saved PyTorch model and use it to make predictions. In this section of the code, we start by including the necessary headers from the libtorch library, which contains the essential components for model management and tensor operations. We then declare a variable to hold our model, indicating that it will be of type torch NN module. This is the base class for all neural network modules in PyTorch, allowing us to manage our model's architecture and forward propagation methods seamlessly. Next, we utilize the torch load function, which retrieves the model from the file PyTorchModel PT that we previously saved. This function effectively reconstructs the model by loading its architecture and parameters directly into the session, making it ready for use without any retraining. Following this, we create a tensor representing our input data. In this case, we generate a random tensor with the shape of 1, 3, which could correspond to a single sample of 3 features. Finally, we pass this input tensor to the model's forward method to make a prediction. This straightforward process allows us to leverage our previously saved model for immediate inference in any deep learning application. In conclusion, we've gone through model serialization APIs available in C++ libraries including dlib, Flashlight, MLPack, and PyTorch. We explored how to save and load models seamlessly, which is an invaluable skill for developers working in machine learning. Model serialization allows you to preserve your hard work and utilize it in various applications, enabling efficient deployment and execution. So far, we've learned how to implement model serialization in dlib, Flashlight, MLpack, and PyTorch, making our workflow smoother and more efficient. In our next session, we will explore advanced techniques for optimizing model performance and enhancing their capabilities. Thank you for tuning in. The ONNX format is a special file format that's used to share neural network architectures and parameters between different frameworks. Today, we will explore how to export and import models using ONNX. This discussion will enable you to leverage ONNX's cross-framework capabilities, facilitating smoother transfers of models between different deep learning libraries and maximizing flexibility in your workflow. So far, we learned about model serialization in various C++ libraries, including dlib, Flashlight, MLpack, and PyTorch. We covered how to save and load machine learning models efficiently, allowing for seamless integration and management in applications. This process is essential for preserving the work done during model training and facilitating easy deployment. In this lesson, we will talk about exporting and importing ONNX models, how to do it, and why it is beneficial for your projects, especially in a multi-framework environment. Now, let's implement the function to export our PyTorch model to the ONNX format. We begin by including the necessary headers for the Torch library. The function export to ONNX accepts two parameters, a model and a file path, as a string where the ONNX model will be saved. Inside this function, we create a dummy input tensor which has the same shape as the input our model expects, simulating a typical image input for a convolutional neural network. This is crucial for the export process to understand the model's architecture. Next, we utilize the Torch, ONNX, export function which performs the core task of exporting the model along with its parameters to the specified file. The argument export params is set to true, meaning we want to include the trained parameters along with the model's structure. After defining the export function, we proceed to the main function, where we instantiate a simple sequential model using a shared pointer. We add a convolutional layer for demonstration purposes before calling our export to ONNX function to save the model as model ONNX. This process illustrates how easily we can convert a PyTorch model into the ONNX format, ready for use in different frameworks. Now let's see how we can implement the load and run ONNX model function, which is crucial for importing an ONNX model and executing it. This function begins by initializing the ONNX runtime environment, which sets the stage for model interactions. Once the environment is ready, we create a session by loading our model from the specified path, preparing it for inference. Next, we focus on preparing the input data. For demonstration, we are simulating input with dummy data, creating a tensor that matches the expected dimensions. This is critical for ensuring that the model receives input in the correct format. We use auth value create tensor to create this input tensor and store it in a vector. In the next step, we execute the model using session run, passing in the input tensors and specifying the names of the input and output. This neatly handles the prediction process. After running the model, we can access the results stored in the output tensors, demonstrating how easily we can retrieve and utilize the predictions made by our ONNX model. Overall, this function encapsulates the essential workflow for importing and running inference on an ONNX model using the ONNX runtime. Next, we will write the following code to import an ONNX model into TensorFlow using Python. We begin by importing the necessary libraries, ONNX for handling the ONNX model and ONNX-TF to facilitate the conversion to a TensorFlow representation. First, we load the ONNX model file named model ONNX using the ONNX load function, which deserializes the model and prepares it for further processing. After loading the model, we convert it into a TensorFlow-compatible format using the ONNX-TF backend prepare method. This step is crucial as it translates the ONNX model's architecture and parameters into a format that TensorFlow can work with effectively. Now that we have our model ready in TensorFlow's representation, we can use it for inference. For testing the model, we create a random input tensor that simulates the shape expected by the model, typically representing an image with dimensions 1x3 x2 24 x2 24. We then call the run method on our TensorFlow representation and pass in the input tensor. This function will execute the model and return the output tensor, allowing us to obtain predictions just like we would with any other TensorFlow model. You will soon realize that ONNX offers not only flexibility, but is also essential for optimizing performance. When you share models across frameworks, you can leverage the unique strengths of each tool. For instance, you might train your model in PyTorch but use TensorFlow's high-performance inference capabilities to deploy it in production. This way you can combine various tools' strengths and make your projects more efficient and powerful. However, there are a few things to keep in mind when exporting and importing with ONNX. First, ensure that the operations used in your model are supported by the ONNX format. While most common neural network layers are supported, some specific or custom operations may not translate directly. Always check the official ONNX documentation for compatibility before proceeding with your model export. Moreover, performance might also vary based on the framework and the underlying hardware. Conduct thorough benchmarks, especially for latency-sensitive applications, to ensure that swapping frameworks yields the necessary speedup without compromising accuracy. In conclusion, exporting and importing ONNX models across different frameworks opens up new opportunities for your machine learning projects. You have the ability to share and optimize your models with greater flexibility, making your workflow cleaner and much more efficient. You learned how to export models from PyTorch using ONNX and import them back into various frameworks with practical code examples to guide you. This understanding fosters a more robust machine learning environment where models can traverse the boundaries of different libraries. As we wrap up today's lesson, remember that being adaptable is key in the rapidly evolving world of machine learning. In our next session, we will delve into advanced techniques for optimizing model performance. Thank you for joining me today, and I look forward to exploring more exciting topics with you in the future. Visualization and tracking systems for machine learning experiments are essential components of the ML development process. They help teams make informed decisions, improve model performance, and maintain organization throughout the experimental lifecycle. So far, we learned about the ONNX format, a universal file system for sharing neural network models between different frameworks, enhancing model interoperability. We discussed how to export models from PyTorch to ONNX using the torch ONNX export function and how to import ONNX models into frameworks like TensorFlow for inference. Additionally, we emphasized the importance of testing and validating these models across different environments while maintaining performance. Finally, we explored the benefits and considerations of using ONNX for optimizing machine learning workflows. Now we will cover visualization and experiment tracking systems, which provide critical insights and streamline the machine learning workflow. When working on machine learning, it can feel like navigating through a maze. You have multiple models, hyperparameters, and datasets, and each change you make can lead to different outcomes. This is where visualization and experiment tracking systems come into play. These systems help you keep track of various experiments, their configurations, and their outcomes in a structured manner. Imagine having a detailed map of your maze, which allows you to find your way quickly without getting lost in numerous experiments. Now let's implement a basic experiment tracking system using C++. The core of our implementation is the experiment tracker class, which is designed to log and display the results of various machine learning experiments. It maintains a private map, experiments, that associates each experiment's name with its corresponding parameters and accuracy. When we log an experiment with the logExperiment function, we pass the experiment's name, a map of hyperparameters, and its resulting accuracy. This function stores the experiment details in the experiment's map, effectively recording the necessary data for future reference. Next, we have the displayExperiments method, which iterates through the recorded experiments and outputs their details to the console. This includes printing the name of each experiment, its hyperparameters, and its accuracy. Such structured logging ensures that we can easily revisit past experiments and analyze what worked and what could be improved. In the main function, we create an instance of the experiment tracker, log 2 different experiments with distinct hyperparameters, and display all logged experiments. This straightforward setup not only illustrates the core functionality of experiment tracking, but also serves as a foundation for more complex systems that can enhance machine learning workflows. Now let's see how we can implement a simple function to visualize the results of our experiments by plotting hyperparameter values against their corresponding accuracies. In our example, we define the function plotExperimentResults, which takes two vectors as parameters, one for hyperparameters and another for accuracies. This function iterates through each hyperparameter and its associated accuracy, then outputs them to the console in a formatted manner. Inside the main function, we initialize two vectors, hyperparams and accuracies, which hold the values we want to visualize. For instance, the hyperparameter values might represent different learning rates used in training, while the accuracies demonstrate the corresponding effectiveness of those parameters. We pass these vectors to our plotting function, which then displays the relationship between hyperparameters and their resulting accuracies. This approach serves as an essential building block for developing more advanced visualization techniques. Although we are using console output here for simplicity, in real scenarios, utilizing a library like Matplotlib in Python would allow us to create dynamic visual plots, enabling deeper insights into the experimental results. Thus, effective visualization can help identify trends and optimize model performance in ongoing experiments. Utilizing both systems together can lead to more informed decision-making. For example, if you notice a drop in accuracy with certain hyperparameters, you can drill down into that experiment's log to analyze the exact settings, allowing you to troubleshoot effectively. You can tweak the hyperparameters and rerun experiments, all the while keeping everything neatly logged. Consider integrating both tracking and visualization into a single workflow. In C++, you can build on the previous example, allowing the tracker not only to log data but also to send it to a visualization component, which could use third-party libraries or a custom implementation. Incorporating information from experiment tracking and visualization can streamline the debugging process. By using visual feedback, you might quickly identify a long tail of poor-performing experiments, allowing you to attribute accuracy dips to specific model settings. For instance, if a graphical representation reveals that a learning rate of 0.1 consistently results in lower accuracy compared to 0.01, you can adjust your experiments accordingly with the confidence that data backs your decisions. As you collect data from your experiments, another crucial step is storing and managing the information effectively. Many teams opt for centralized tracking tools such as MLflow, TensorBoard, or weights and biases, which can automate much of the logging and visualization processes. While each tool has its unique features, understanding the aspects of tracking and visualization allows you to choose based on your needs. For instance, say you have a large team collaborating on various models. Using MLflow could let everyone log their results in one shared repository. These tools often come equipped with APIs that simplify logging and provide robust visualization out of the box, so you spend less time coding and more focusing on the science of your models. In conclusion, visualization and tracking systems are fundamental in the machine learning workflow. They both complement each other. Tracking systems maintain rigorous records of experiments while visualization transforms complex data into accessible insights. As you progress in your machine learning journey, investing time in understanding and implementing these systems will enhance your experiment's reproducibility and effectiveness. So, as we've highlighted today, managing a multitude of experiments doesn't need to look like a chaotic pile of spaghetti. Instead, it can be orchestrated harmoniously, giving you the clarity needed to innovate and excel in your machine learning endeavors. In this tutorial, we're diving into the world of experiment tracking using the MLflow REST API. This powerful tool helps us organize and monitor our machine learning experiments with ease. So far, we've learned about the importance of visualization and experiment tracking systems in machine learning, which help organize and analyze various experiments. We discussed how these systems record essential details, facilitating reproducibility and performance auditing. By utilizing both tracking and visualization, one can gain insights into trends and correlations, leading to informed decision-making. Lastly, we emphasize the value of centralized tools for logging and visualizing results to streamline the workflow. Now, we will focus on implementing experiment tracking with MLflow and explore how to leverage its REST API. With MLflow, you're equipped to streamline your machine learning workflows. It provides not just tracking of your experiments, but also capabilities for project management, model management, and delivery. In this episode, we will learn how to interact with the MLflow REST API to manage our experiments, log parameters, metrics, and models, all via simple HTTP requests. Let's kick things off by first setting up MLflow so that you can start using the API. Next, we will write the following code to install and launch the MLflow tracking server. First, you need to ensure MLflow is installed on your system. You can do this seamlessly using the pip package manager. After installation, we launch the MLflow server using a command that starts the tracking UI, accessible at http://localhost 5000. This interface serves as a visual tool to monitor and manage your ongoing experiments and allows us to interact with MLflow through its REST API. Now, let's implement the following C++ code for creating a new experiment via the MLflow API. We will use the CUIL library to facilitate HTTP requests. The createExperiment function initializes a CUIL object and constructs a JSON string for the experiment name. By setting the appropriate URL for the API endpoint, we prepare our POST request to create the experiment on the MLflow server. After executing the request, it checks for errors to ensure the experiment is successfully created, and finally, it cleans up resources to maintain efficiency. This basic setup is foundational for further exploration of MLflow's capabilities. Now let's implement the following function to log parameters for your machine learning experiments. This method named logParameter takes three inputs: the run ID, the parameter name, and the parameter value. First, the function initializes CURL, which is a library used to make HTTP requests. After setting up, it constructs a JSON string that includes the run ID, parameter name, and value we want to log. This JSON payload is essential because it formats the data appropriately for the MLflow REST API. Next, we specify the URL of the endpoint responsible for logging parameters, which is API runs log parameter. We then pass the JSON data using the curl easy setup function. The callback function curl easy perform is executed to send the request, and if there's an error, it will be printed to the standard error output. Finally, we clean up our CURL resources to ensure we do not leak memory. This function plays a crucial role in documenting how your models are configured, helping to track and understand the different parameters affecting your experiment outcomes. Now let's implement a function to log metrics, which is crucial for assessing the performance of your machine learning models. The function begins by initializing a CURL object, allowing us to make HTTP requests to the MLflow API. We set up the function to accept parameters such as runId, metric name, metric value, and an optional timestamp to denote when the metric is recorded. Next, we craft a JSON string that encapsulates these parameters in the required format for the MLflow API. The URL http://localhost 5000/API/20/run/log metric is specified to direct the request to the appropriate endpoint for logging metrics. We make use of curl easy setup to set the URL and post fields, which hold our JSON data. After making the request with curl easy perform, we check for any errors, logging messages to the console if something goes awry. Finally, it's important to clean up the CURL resources to avoid memory leaks. Monitoring your metrics throughout training will give you valuable insights into the model's performance improvements or regressions, further emphasizing the importance of this logging process. Now let's implement the functionality to log artifacts using the MLflow API. The logging function starts by initializing a CURL object, which is essential for performing HTTP requests. We set up the necessary parameters, taking in the runId and the path of the artifact we want to log. The JSON string is formatted to include these values, which are crucial for identifying the specific run and its associated artifact. Next, we configure the CURL options, specifying the URL endpoint for the artifact logging and passing in the JSON data as the payload. After executing the request with curl_perform, the function checks for potential errors that may arise during the transmission. If any errors occur, the function will print the corresponding error message to the standard error output. Finally, we ensure to clean up by releasing the CURL resources to prevent memory leaks. This implementation is important as it allows you to document essential files generated during your experiments, such as model files or visualization plots, thereby facilitating better sharing and version control of your machine learning models. Now let's take a look at how we can retrieve all the runs associated with a specific experiment using the MLflow REST API. We begin by defining a function named getExperimentRuns, which takes the experiment ID as a parameter. First, we initialize the CURL library, which is essential for making HTTP requests in C++. Once initialized, we dynamically construct the URL that points to the API endpoint for fetching runs related to the given experiment ID. Next, we set the necessary CURL options. The URL is specified using the curl_opt_url option, and we indicate that this will be a GET request by setting curl_opt_http_GET to 1. After preparing the request, we call curl_perform, which executes the HTTP request for us. This is where we fetch the details of all runs for the specified experiment. If the request is successful, we will receive the run details, which can then be processed further for analysis or visualization. Lastly, we ensure to clean up the CURL resources to avoid memory leaks. This method encapsulates how easy it is to access logged experiment data, allowing you to delve deeper into model performance metrics and parameters. In advanced scenarios, you can even set up an automated pipeline where these API calls are made in response to conditions in your workflows. Imagine running experiments continuously in the cloud and automatically logging performance metrics without manual intervention. This scalability is a game changer in machine learning research and production. As machine learning practitioners, having robust experiment tracking mechanisms is invaluable for model optimization. Not only do they help us to meticulously document findings, but they also enhance reproducibility, allowing us to return to experiments with full confidence in the logs. In conclusion, we've covered a lot of ground on experiment tracking using MLflow's REST API. We've highlighted how to set up MLflow, create experiments, log parameters, metrics, and artifacts, and retrieve runs. By integrating these capabilities into our machine learning workflows, we not only ensure better organization, but also gain insights to enhance our models continuously. So take these code snippets, spin them up in your own projects, and start embracing methodical experiment tracking today. Happy logging! To deploy machine learning models on mobile devices, particularly those running on the Android operating system, we need to understand the entire lifecycle of moving a trained ML model from a robust computing environment into a resource-constrained mobile environment. In this lesson, we'll dive into the essential considerations and practical steps for successfully deploying machine learning models using C++. So far, we covered tracking machine learning experiments using MLflow, where we learned how to set up experiments, log parameters, metrics, and retrieve results through API calls. Now, we will explore deploying ML models, specifically focusing on creating an object detection application for mobile platforms using C++ and PyTorch. To kick things off, it's important to note that mobile devices have unique constraints compared to computers. The limited processing power, memory usage, and battery life are key considerations when deploying models. For instance, running large-scale deep learning models directly on a mobile device is usually infeasible. Therefore, we typically opt for lightweight models, such as the YOLOv5 architecture, which balances speed and accuracy for tasks like object detection. Before we set up our mobile application development environment, ensure that you have Android Studio installed along with the Android Software Development Kit, SDK, and the Android Native Development Kit, NDK. These tools will allow us to develop applications utilizing C++ for performance-critical components, while simultaneously leveraging the Kotlin programming language for interfacing with Android APIs. Now let's see how we can build the PyTorch library specifically for the Android environment. We begin by navigating to the desired directory and cloning the PyTorch source code from GitHub. This allows us to work with the latest version, which we can pin to a stable release through a checkout command. To ensure smooth compilation, we also initialize any necessary submodules. Next, we need to set up our environment variables to point to the Android Native Development Kit (NDK) and specify the target architecture, which is ARM 64-bit in this case. The shared library option is enabled to produce dynamic libraries that the Android app will link against. We additionally disable Vulkan support, simplifying the library for mobile use. Finally, we invoke the build script with various flags that fine-tune the compilation process, such as excluding CAF2 mobile support. By executing this series of commands, we configure the build system, allowing it to generate architecture-specific libraries that can be integrated into our Android application, thus setting the foundation for deploying machine learning models on mobile devices. Now that we have outlined the structure of our Android application, let's delve into how we will integrate our object detection functionality using C++. First, we will create a class called Object Detector. This class is essential for loading our YOLO model from a specified path, which is necessary for making predictions on the images captured by our mobile device's camera. The constructor of the class utilizes PyTorch's torch JIT load function to load the model, making it readily available for inference. Next, we will implement a detect method within the class. This method will take an OpenCV image as its input, perform necessary preprocessing, run inference with the loaded model, and finally handle the post-processing of the results. The goal here is to ensure that the inputs are formatted correctly for the model and that the outputs align with our requirements for object detection. By encapsulating this functionality within a class, we promote cleaner code and make it easier to manage state and functionality related to our object detection process. This organization will be crucial as we expand our application's features and refine the detection capabilities. Next, we will implement the process of obtaining and preparing the YOLOv5 model for our mobile application. To do this, we'll first clone the YOLOv5 repository from GitHub. This repository contains all the necessary files and configurations for the YOLOv5 model, which is lightweight and particularly suited for mobile scenarios. After cloning the repository, we navigate to the newly created directory and install the required dependencies as specified in the requirements txt file. Once the dependencies are installed, we will generate the torch script model using a specific export command. This command will optimize the YOLOv5 model for mobile deployment by converting it to a format suitable for quick inference on devices. The generated file, YOLOv5's torch script, contains the optimized model, which we will place in the Assets folder of our Android project. Additionally, we need to provide a class labels text file that will map class names to their corresponding identifiers, ensuring that our model can correctly identify objects during detection. This step is crucial for creating an efficient object detection application on mobile platforms. Now let's delve into the implementation of our object detection model using C++. The first important step is defining a class named Object Detector, which serves as the foundation for our model interaction. Within the constructor, we initialize the model by loading it from a specified path. This allows us to utilize the pre-trained YOLOv5 model for object detection tasks. Next, we focus on the detect function, which will eventually accept an image as input. In this function, we plan to include preprocessing steps that prepare the image for inference, such as resizing and normalizing pixel values. This is crucial because the model expects inputs in a specific format. The inference process will follow, leveraging the loaded model to predict detected objects in the input image. We also declare a private member variable, model, which holds the instance of our loaded YOLO model. This class structure not only organizes our code but also encapsulates the model's functionalities, making it easier to manage and extend as needed. This setup lays the groundwork for efficient object detection in our mobile application, ensuring that we can integrate machine learning smoothly with C++ and Android. Now let's implement a function that converts an image from the OpenCV format to a PyTorch tensor. This process is critical for ensuring that our image data is compatible with the PyTorch model we are using for object detection. We start by defining a function that will take a constant reference to a CV, mat image. The first crucial step is to assert that the image has 3 channels, indicating it is in RGB format, as our models expect this specific format. Next, we leverage PyTorches from blob to create a tensor directly from the image data. Here we specify the shape of the tensor, ensuring that it reflects the dimensions and channels appropriately, converting the image data type to bytes. Following this, we normalize the pixel values by converting the tensor to floats and dividing by 255 to scale them between 0 and 1. An important transformation occurs with the permute function, which rearranges the tensor's dimensions to fit into the structure that PyTorch requires: batch size, channels, height, width. Finally, we clone the tensor to safeguard its contents and return it, ensuring that subsequent operations do not inadvertently modify the original image data. This function sets the foundation for seamless image processing for our object detection tasks. Next, we will implement the process output function that handles the results from the object detection model. This function takes an output tensor as input, which contains the detection predictions from the YOLO model. The first step in the implementation is to iterate through each detection contained within the output. Inside the loop, we extract the confidence score, which is stored at the 5th index of each detection. This score indicates how confident the model is about the detected object. We compare the confidence score against a predefined threshold value referred to as conf threshold. If the score exceeds this threshold, it signifies that the detection is considered valid and worth saving. Currently, the code includes a placeholder comment where you can implement logic to store these valid detections for further processing. This is a critical step, as filtering out low confidence detections helps to enhance the overall accuracy and quality of the object detection results. Additionally, while not shown here, further logic would typically follow to apply non-maximum suppression, NMS, and eliminate duplicate detections by focusing on the highest scoring bounding boxes, ensuring that we have clean and reliable outputs for our mobile application. Now let's see how we can initialize the object detection within our Android application. The initObjectDetection function is declared as an external Kotlin function that allows us to call native C++ code directly. This setup forms the bridge between our Kotlin code and the C++ components that manage the machine learning model. In the main_activity class, we override the onCreate method, which is called when the activity is first created. Here we invoke the super onCreate saved instance state to ensure that the parent class's setup is executed properly. Following this, we would typically set up the user interface, request camera permissions, and prepare the camera for capturing images. To kick off the object detection process, we call the initObjectDetection function, passing it a camera ID, here 0, denoting which camera to utilize. This is essential as it directs our application to start processing frames from the specified camera. By linking these components together, we lay the foundation for seamlessly integrating Kotlin and C++, which is crucial for successfully deploying our object detection model in a mobile environment. As we wrap up this lesson, we have taken a deep dive into deploying ML models specifically for mobile devices. We covered building our environment, utilizing PyTorch for efficient model loading, and using C++ and JNI to integrate with Android's camera capabilities. Our implementation of an object detection application demonstrates how to move from model development to deployment on a mobile platform. Keep in mind that this is just the tip of the iceberg. The world of deploying machine learning on mobile devices is vast and filled with opportunities for optimization, enhancement, and new feature creation. Remember to continuously refine your applications based on user feedback and performance metrics, always striving to enhance the user experience while maintaining efficiency. Now go ahead and experiment with deploying your models and see what exciting mobile applications you can create. Now let's see how we can configure our Android application to utilize the device's camera. To begin, we need to add the necessary permissions in the Android manifest XML file. By including uses permission Android name equals Android permission camera / and uses permission Android name equals Android permission write external storage / we allow our app to access the camera hardware for reading video feeds and, if needed, saving images. Next, we will implement the main activity of our application. Here, we check whether the camera permissions have been granted upon application launch. If permissions are granted, we can safely call the OpenCamera function to establish a connection with the camera. In case permissions are not granted, we request the camera access from the user. This approach ensures a smooth user experience by avoiding crashes due to missing permissions. Moving forward, we will set up the camera preview. By creating a surface view, we can display the camera feed on the screen. This involves initializing the surface holder and defining its callback methods, which allow us to manage the camera lifecycle effectively. Once the surface is created, we start the camera preview, ensuring we clean up by stopping and releasing the camera when the surface is destroyed. Next, we will implement the function setCameraPreview, which is crucial for setting up the camera preview on our surface view. This function begins by obtaining a reference to the surface view defined in our XML layout using FindViewById. We then acquire the surface holder, which allows us to manage the life cycle of the surface view, particularly when it is created, changed, or destroyed. Now let's see how we can handle these lifecycle events by adding a callback to the surface holder. When the surface is created, we'll set the camera's display to the holder and start the camera preview. This is where the camera begins capturing frames for our object detection application. It's important to note that managing this lifecycle correctly is fundamental. Next, we also implement the surfaceChanged method to handle any changes in the surface's dimensions, even though we'll leave it empty for now. Finally, when the surface is destroyed, we ensure to stop the camera preview and release the camera resources to prevent memory leaks and ensure the app operates efficiently. This careful management of resources is key in any real-time application. Now let's implement the method onCameraFrame, which will be triggered whenever a new frame is ready from the camera. In this function, we convert the captured frame, represented as a byte array, into a format that our C++ function can process. By calling processFrameNativeFrame, we send this frame to the native layer where the object detection logic resides. Next, we'll examine the C++ function, processFrameNative, declared with JNI to ensure proper communication between our Kotlin and C++ code. Inside this function, we start by extracting the byte array data from the incoming Java array with getByteArrayElements. This raw byte data is then converted into an OpenCV-mat object, enabling us to manipulate the image easily. We convert the image format from RGBA to RGB, which is essential for our YOLOv5 model to perform accurate object detection. After preprocessing the image, we invoke Object Detector detect_img to run our detection algorithm. Once the detections are complete, we need to ensure that we properly release the byte array back to the Java environment with release_byteArrayElements, maintaining memory efficiency. This step is crucial for preventing memory leaks and ensuring our application runs smoothly during real-time detection. Now let's implement the following code to visualize the detected objects on our camera feed. We begin by iterating through the detection results, which contains information about the detected objects and their confidence scores. For each detection, we first check if the confidence meets a specified threshold. This helps filter out any low-confidence detections that may not be accurate. Once the confidence criterion is satisfied, we extract the bounding box coordinates for the detected object. Using the CVRectangle function, we draw a rectangle around the identified object on the image, using a green color for visibility. This rectangle indicates the location of the detected object within the frame. Next, to provide additional context to users, we create a label that combines a static text with the object's class ID. We employ the CVPutText function to overlay this label just above the bounding box in a blue color, making it easier for viewers to understand which objects have been detected. This enhances the visual feedback on the camera feed, allowing users to not only see where objects are located, but also what those objects are. Now let's implement a frame skip mechanism to optimize our real-time object detection application. In this approach, we maintain a frame count variable that increments with each incoming camera frame. The key here is to only process frames that are multiples of a predefined frame skip interval. This means that for every frame skip interval frames, we perform object detection while the others are simply skipped. By doing this, we can significantly reduce the processing load on the device, allowing for smoother operation and minimizing lag during detection. This balance of performance and accuracy is crucial in real-time applications, as consistently processing every frame can lead to performance bottlenecks. As a result, our application will remain responsive, ensuring that users experience quick and efficient object detection without compromising on accuracy. This remains an essential aspect of our implementation as we continue to refine our application for optimal performance in diverse environments. Next, we will implement a loading indicator to enhance user experience while the model processes the video frames. In this case, we will use a progress bar in the layout, which is a commonly used element for indicating ongoing operations. The attributes defined for the progress bar specify that it will be centered on the screen and initially set to be invisible. When the model begins processing frames, you'll need to ensure that the progress bar is displayed, letting users know that the application is still active and working on their requests. It's important to toggle the visibility of this progress bar to visible while processing occurs and back to gone when the processing is complete. By doing so, you maintain user engagement and prevent the impression that the application has frozen, which can significantly improve the usability of your real-time object detection app. This visual feedback is a small yet critical aspect of app development, particularly in real-time applications, as it aligns with best practices for user experience design. As we reach the end of our exploration, don't forget the importance of testing and iterating on your implementation. Real-time object detection on mobile devices isn't merely about getting it to work. It's about refining it to handle various environmental conditions, lighting, and different camera resolutions. Test thoroughly under different scenarios: low light, fast-moving objects, and varied distances. Assess performance and accuracy and make adjustments to your approach based on your findings. Real-time object detection is a dynamic field, and staying adaptable is key. In closing, we have constructed a powerful Android application capable of real-time object detection using PyTorch and YOLOv5. From setting up the camera to processing frames and visualizing detections, we covered the critical components to bring this technology to life on mobile devices. In future projects, consider expanding the app's capabilities. Maybe you'll want to implement features like object tracking, alerting users when a specific object appears, or even integrating with other sensors on the device. The possibilities are vast, and technology is at your fingertips. Go forth and create.